Right. Good evening, good evening, good evening. Welcome back to one more session of your WOC. This is your Vani ma'am. This is your world of chemistry. All right. To all the students who are going to write the exams in almost 6 days, nothing to worry. All right. As you all know, world of chemistry has been with you all since 6 to 7 years, and it is also famous for its organic chemistry in 3 days. Now it's the time for me to help you back with the organic series. Very important. Normally what happens, students, before the exam we tend to bite our nails and say, God, I don't know anything, I forget everything. How much ever I practice in organic chemistry is tough. Let me tell you a secret. Organic chemistry is the easiest one of everything. You all know, for your board examination, organic chemistry weightage for all the chapters starting from your haloalkenes and haloalkanes, haloarenes to your biomolecules. How much is the weightage? Yes, you all know this. It's almost 33 marks. Yes, 33 marks. Oh my God. If I study this 33, obviously 33 is easy to get. Compared to your physical chemistry and compared to your inorganic chemistry, because organic chemistry is something, if you know the logic, you can apply it anywhere. So I am there, no, leave it to me, it's okay. Yes. Now important thing, I am going to start with this haloalkanes, then gradually go to your alcohols, phenols, then gradually go to your aldehydes, ketones, acids, gradually go to your amines, and gradually I will go to your biomolecules. But to know or to study all this, what should I do, ma'am? Simple. Only thing, having confidence in yourself. And most important thing, give your best, do your hard work and believe in that hard work. So now it's time for us to start your chapter, that is nothing but your haloalkenes and haloarenes. Before this, again I'm stressing, students, WOC or World of Chemistry has all 100% videos for your grade 10th, grade 11th and grade 12th. Yes, grade 12th, if I have to talk, you have your first unit 10, that is haloalkanes and haloarenes. Since this unit is, if I have to tell you, it's a cakewalk. It's easy. Haloalkanes and haloarenes, the weightage of the chapter is only 6 marks. Now what am I going to do? As I said, Vani ma'am is not going to leave your hand. So I have taken out your NCERT and line by line, I have prepared MCQs. I have prepared 1 mark questions, I have prepared 2 mark questions, I have prepared 3 mark questions, and important 4 mark case based questions, as well as 5 mark long answers. Where did I leave? Nothing I left. Nothing. Everything is covered in the series. So haloalkanes and haloarenes, as I said, this particular 5 days or 6 days, you should promise me that you will watch the complete video. Ma'am, if I watch this, is this enough? Yes, it will be 100% enough. Why? Because every line of NCERT is picked. It is almost torn into pieces and made a question. Okay, so follow this. So what I'll do is, I'll teach you the topic first. Then I'll take you to the related questions which are asked. From the basic thing to the advanced questions. This will be useful for your NEET examination, JEE also, but CBSE level wise I have done. Topic is taught, then I will take you to the question and I will try to explain everything. MCQs, I will give the question. I'll give you the page number of NCERT. I will solve the question and you will understand it. Yes, like that, 1 mark, 2 mark, 3, 4, 5. How to write in the exam also I'll tell you. But only thing is, you need to follow the complete video. If it is a 3 hours video, you need to completely watch, then only you'll understand. Suppose if any certain questions are missing also, I will send you in the Telegram. That also will cover everything. So you are going to join me in this organic series, as we did organic chemistry in 3 days, which was a huge hit. Like that, this organic chemistry in these 6 days, we are going to rock it. That's possible only with your support. So let us not waste time. Watch the complete video, topic thought thoroughly, MCQ 1, 2, 3, 4, 5. Everything is taught in detail. But you should take a book and start listening to the video and understanding and noting it. Any doubt at any point of time, please ask me. I am there available in the Telegram. I am there in the comment section. I am there with you all always. Correct? So let's start the video. All the best. Let's start with the first chapter, that is Unit 10, haloalkanes and haloarenes with a smile. Thank you. Let's start. Watch the video till the end, okay? And before going, one more new channel I have started, that is Motivation with Mani Putepalli. Watch that. There we are going to discuss a lot of life skills, soft skills. We are going to listen to the stories. Beautiful it will be, okay? Right, chalo. Let's not waste time. Let's start the video. All right. So, welcome back, students. As we have discussed, we are going to start your complete organic chemistry revision series for your boards 2025. I know all are in lot of tension. Nothing to worry. Relax. And first, before we start the series, I want all of you to just smile. Yes, this beautiful smile is going to relieve your tension. Alright. So all those who are connected for the first time, thank you so much. And all those who are there with me since long, God bless you all. Promise me you're going to stay with me throughout and you're going to watch the complete video. Yes. So we are going to start with your organic revision series. Yes. Ma'am, revision series means you'll be doing all on like little and little. No. I'll show you how I'm going to do. As you all know, for your 2025 board exams, you have haloalkanes, arenes, alcohols, aldehydes, amines and biomolecules. Total your weightage for organic is 33 marks. OMG. So we are going to work for this. Every mark of this is very important for us. You all know inorganic chemistry is for 14 marks and physical chemistry is for 23 marks. Don't worry. Organic is the easiest part of all the three. So we are going to work hard to get this 33 and the responsibility is mine. Alright? Yes. So this is your Vani ma'am starting with your topic. As you all know, for the 2025 board exam, the pattern of the paper is like this. It has 33 questions. You have 1 mark questions, 2 mark questions, 3, 4 and 5. What are we going to do? I'm going to train you in all this variety. Yes. I also request you to please join the Telegram channel because you will have all the notes in the Telegram channel also. So careful to join immediately and the link of the Telegram is given in the description as well. Alright? Okay. So now we are going to start haloalkanes and haloarenes, that is unit 10. The total weightage is how much? Total weightage is 33 marks for the whole of organic and this is my assurance. Okay. So first of all, points to remember, I'll be dealing such questions. Yes, such questions. What is this? So a lot of questions rather. Every page of your NCERT is marked and from that page of NCERT, a question is framed in this way for you all. So carefully follow the complete video, full video so that it is easy for you all. What am I going to do? I'm going to teach you the topic first. Okay, slowly. After I teach the topic, that means everything is 100%. Once I teach the topic, I'm going to take you to the questionnaire, whether it is MCQ question, whether it is 1 mark question, whether it is 2 mark, as I said, whether it is 3, whether it is 4, whether it is 5. All the varieties questions are covered in this video. So if you watch this video, completely your haloalkanes arenes will be done. Like this, I'll be doing alcohols, I'll be doing everything. Okay. So let me check whether my video is getting recorded or not. Otherwise, it will be the problem. Okay, yes, it is getting recorded. Alright, I need to check in between, right? Alright. So let's start the video. First chapter, points to remember. Yes, let's start. In your haloalkanes and haloarenes chapter, whenever you're doing, as I said, you need to first know your basic complete chapter. What is the flow chart? Okay, I'll be doing the flow chart. After that, after doing the flow chart, gradually I'll be taking into topic wise discussion. Topic wise discussion is what I'm going to do. Topic wise discussion in detail. Once I do the topic wise discussion, so I request all of you, if you want your classroom type video lecture, yes, if you want that, you can watch one-shot videos which I did and kept in the playlist. One-shot videos are already there. Yes, it is just like your classroom. Your Vani ma'am is teaching on the board and you can watch that. Okay. Then I'll be doing the questionnaire, what is there which is required for your boards. Let us start the first thing. So in your haloalkanes and haloarenes flow chart, you are supposed to learn, because I'm using my writing pad, I'll be writing, just drawing an arrow. You need to learn compulsory classification based. Okay, you need to learn what is a classification for the board exam and related questions. After classification, you're supposed to learn a nomenclature of a particular chapter. This is compulsory. After that, you need to learn nature of CX bond. Okay, nature of CX bond. Your carbon halogen bond, this is what you're going to learn. In that you have different reactions, alcohol reacting with HX, like that. A lot of reactions are there. Everything I'm going to explain. And after that, you are also going to learn basically methods of preparation. Okay, so methods of preparation of haloalkanes and haloarenes, methods of preparation. In that methods of preparation, what are there? You're going to learn from alcohols. Okay, you learn how you're preparing from alcohols. You're learning from hydrocarbons. You're learning a reaction from halogen exchange reaction, then you are going to learn, okay, sorry, my writing pad little bit got disconnected. I'm just trying to check it. It sometimes bothers me. Okay, so halogen exchange reactions. All right, okay, halogen exchange reactions. After that, 1 second, sorry for the inconvenience. Okay, halogen exchange reactions. Then you have your physical properties. After that is over, you are going to learn your physical properties. In physical properties, what will we learn? We will learn boiling point concept. We will learn melting point concept. We'll be learning solubility concept. All this we'll be learning. Everything I'm going to teach. So once your methods of preparations are over, once your physical properties are over, once your basic things are over, then I'll take you into a concept called reactions. Reactions of both HA means haloalkanes, reactions of your HR, haloarenes also, or HA or HR. Haloarenes is what I write. So basically in reactions of HA, you are going to learn, I'm going to teach you the mechanisms, SN1 reactions, related questions, SN2 reactions. Then I'm here in haloarenes, I'm going to teach nucleophilic substitution reactions, and I'm also going to teach electrophilic substitution reactions. That's all, ma'am? No, that's all. No, we still have concepts. Careful, that too, there are a lot of concepts like chirality concepts. Yes, very important. Along with these reactions, we also have elimination reactions that we should know compulsory. We also should know substitution means basically reaction with metals is one more reaction with metals. This is also there. This also we are going to study. Along with this, we are going to study the concept of chirality. Yes, chirality concept is very important. So I'm going to cover all these concepts, polyhalogen compounds also, and take you into the complete questionnaires. All are covered. Everything is covered. Let's start the video. Now, as I said, haloalkanes and haloarenes, what is important, students? We are going to do NCERT line by line questions. So, line by line questions, and line by line topic. Let us start. First concept. First of all, what actually is a haloalkane or what actually is a haloarene? So, I need to learn the topic first, then only I can answer the questions. First, haloalkanes, let us write here, haloalkanes. Okay, what is the other name given for haloalkanes? They are also called as alkyl halides. Why are they called this? They are called this because when I take an aliphatic hydrocarbon, ma'am, what is aliphatic? HC means hydrocarbon. What is aliphatic hydrocarbon? Let us take CH4. Okay, this is an aliphatic straight chain hydrocarbon. Now, I am going to, just careful, I am going to replace hydrogen with a halogen. I am going to replace hydrogen with a halogen. Now, what will I get? I take out one hydrogen, I add one more halogen, I get CH3Cl. Okay. What is this called? I have little cough, don't mind. This is called methyl chloride. This is my aliphatic. Same thing, what are aryl or haloarenes called? Haloarenes are also called as, yes, they called as aryl halides. Why are they called aryl halides? Because when you take an aromatic hydrocarbon, here I took aliphatic, here I am going to take aromatic. Aromatic means ring carbons, aromatic hydrocarbons, just like your benzene. Aromatic, I took this. What am I doing now? I am going to take hydrogen out and I am going to add one halogen in. Then it will become an aromatic hydrocarbon, that is your haloarene. Yes, haloarene, aryl halide. Yes, aryl halide or haloarene, bromobenzene. Yes, don't say benzene bromo, it is bromobenzene. Easy? Very easy. This is the basic introduction. Now, we have to study after the basic introduction classification, because if I understand this only, I can do the questions further. Correct. Now let us start the classification. CALLIFICATION. Classification. Classification based on what? On the basis of number of halogen atoms. Now we studied your this one, right? What did we study? We have studied what are haloalkanes, what are haloarenes. Now, if one halogen atom is present, if there is only one halogen atom in your haloalkane, that is called monohaloalkane. Monohaloalkane, only one. Like similarly, if two are present, then it is called dihaloalkane. No, same thing, monohaloalkane or monohaloarene. Okay, arene, both. If two are present, it is called dihaloalkane or arene. Same thing, if three are present, three halogen atoms are present, then it is called trihaloalkane or haloarene. Easy, easy. Let us take one example and understand this. For example, for mono, see this, C2H5X. This is mono. Only one halogen atom is present. Correct. Same thing, if I take a benzene ring, if I add an halogen to this, this is monohaloalkane. Alkane. And this is called monohaloarene. Correct. Same like that, dihaloarene means two halogen atoms are present in this, so it is called dihaloarene. This is easy. Dihaloarene. Nothing much questions are asked, but you should understand this. Now further after this classification, monohalogen atoms, further classification. So gradually this is where questions are asked. Let us see. Monohalo compounds or monohalogen compounds or monohalo compounds, there are again further divided. This is where the question arises. Careful. Here monohalo compounds means one halogen atom. The compounds where they are containing compounds containing CAITIN containing sp3CX bond. Carbon means the bond is single bonded there. sp3 hybridization and the carbon CX bond is present. CX bond. Same here like that, you have compounds containing same, I am not writing completely, sp2 hybridized CX bond. Here sp3 hybridized bond, here sp2 CX bond. And what is this now? We will take certain examples and see. Okay. So for sp3, see here sp3, first thing I am taking, this is called primary alkyl halide. I am explaining the concept and then I'll take you to the questions. Primary alkyl halide means what? Your R is bonded to C, H, H and X. Now how many hydrogens are there? There are in primary, there are two hydrogens. Next like that, secondary, shall we take one example here? Okay, we'll take CH3, CH2, Br. This is one primary. Like that, secondary alkyl halides. Secondary alkyl halides, what do you have in this? You have carbon, you have only sorry, you have a carbon attached to one alkyl group, two alkyl groups and your X. And careful, there is one hydrogen in this. There are two hydrogens here, one hydrogen. Example, CH3, one alkyl group, CH3, one more alkyl group, one hydrogen and one Br. This is secondary. Same like that, tertiary alkyl, tertiary. If I take tertiary, now what is here? There are no hydrogens, all are alkyl group and one halogen. For example, here in this case, it is your CH3, all alkyl groups are there and you have your halogen. This is tertiary. Okay, easy. Now same thing, if I have to talk about your understand carefully. In primary there are two hydrogens, secondary one hydrogen, tertiary no hydrogens. Same like this, if I take sp2 hybridized. Now first thing in this vinylic halide. Okay, vinylic halide means, careful, I'll show you the examples, you will understand. In vinylic, careful, see here, in this case your halogen, this is halogen. Halogen is bonded to carbon-carbon double bond. It is bonded directly. In vinylic, halogen is bonded directly to the carbon-carbon double bond. Let us take one more example. In this case, halogen is bonded to a carbon atom where there is a double bond. That is vinylic. One more example I'll take. There is halogen directly bonded to the double bond, vinylic. One more example I'll take. There is halogen directly bonded to double bond. See this. In this case, halogen is directly bonded to the double bond. That is called vinylic. That is all sp2 hybridized. Same thing, if I take sp3 hybridized, those are called aryl halides. What are they called? Aryl halides. Aryl halides means, in this case, what? You have the halogen atom attached to the benzene ring, which is already having a like aromaticity or alternate pi bonds. Okay, aryl halides, once again, you have your benzene ring. In this, the halogens are attached to the benzene ring. These are called aryl halides. These are all sp2 hybridized carbons. So sp3 are primary, secondary, tertiary. sp2 are vinylic, arylic. Anything else, ma'am? Yes. There is one more category for sp2. You need to remember, those are called allylic halides. What are they called? Allylic halides. So sp2, that is over. One more category. Here in allyl, it is halogen is bonded to, careful, X is bonded to sp3 hybridized carbon. sp3 hybridized carbon. What is this? But what is the difference? I'll show you. In allylic, the halogen atom is not directly bonded to double bond. It is indirectly bonded to the double bond. See here, double bond is here. There is one CH2 group and this is called allylic carbon. This is called allylic carbon. So this is sp3. Now one more I'll show you. In this case, your CH, whatever X is there, it is not directly bonded. There is a pi bond. There is a bond, then a double bond. And this is carbon. One more. So this one is called allylic carbon. What is this called? This is called allylic carbon. Easy. Okay, one more example. Okay, I'll take allylic bromide, allyl bromide or allylic bromide. See here. Now what am I doing? I have to draw a double bond, then I have to draw a single bond, then this is called allylic bromide. Alright, one more sp3. One more is called benzylic halide. Benzylic. Carefully understand. If you understand the concept, it is easy for us to solve the question. What is benzylic? Now you only tell me whether it is sp2 or sp3. This is my benzene ring. Okay. Now there is a CH2 bond. Then to this it is Br. Now see here. Bromine is attached to CH2 and what is this called? This is benzylic carbon. What is the hybridization? This is called benzylic carbon. What is the hybridization in this case? It is sp3. Now one more I'll do. One more I am adding CH2Cl. Now what is this? It is attached to CH2. This is which hybridization? sp3. Simple. So primary, secondary, tertiary, allylic, benzylic, then vinylic and your arylic halides. Over. Now let us start with the concept. Let us start with the question first. See the question. Haloarenes containing halogen atoms attached to which hybridized carbon atom? In haloarenes containing halogen atom. Okay, haloarenes itself, they are attached to which hybridized carbon they are asking. Okay. So basically haloarenes. Okay. Now see here. This is my haloarene. Correct. Alright. It is there was one chlorine atom, halogen atom attached. Now you tell me in haloarene it has alternate pi bonds. It something looks like this, right? If I open that and see, now when I see this, it has alternate double bond. Now when it is attached to a double bond means which type of hybridization this is? It is sp2 hybridized carbon. This is haloarene. Correct. Now in haloalkane, if I see, it is all single bonds, hydrogen, hydrogen, hydrogen and chlorine.
Here what is this hybridization? sp3. That means in haloalkane it is sp3 hybridization. In haloarene, what is the hybridization? It is sp2 hybridization. Easy? Very easy question. So gradually understand it. Concept is easy. Alright. Now next question. When two halogen atoms are attached to same carbon atom, then it is called, this is NCERT page 292. When two halogen atoms are attached to the same carbon atom. Okay, easy, simple question. See here, there are two varieties of halogen atoms. Means two varieties. Suppose if it is attached like this to two different carbon atoms, it is called vicinal halide. Vicinal means two different carbons. If it is attached to the same carbon atom like this, then it is called gem or geminal halides. Geminal halides. Now you see, when two halogen atoms are attached to the same carbon atom means, what is it called? It is geminal halide. Easy? Let us go to the next question. Hope the concept is clear, students. Let us go to the next question. Which of the following, little by little, it will become little bit tough, but don't worry, it's easy. Which of the following is secondary halide in this? Secondary, basically. They have given different. Let us draw all. You all know what is primary, secondary, tertiary, right? Okay. First of all, they have given me isopropyl chloride. Okay. What is isopropyl chloride? First one. This is okay. Propyl group means your halogen is attached to the secondary carbon atom. And this is, so this is secondary. Secondary means what? This has only one hydrogen atom. One hydrogen atom is second. That is what we studied. So this is second, 2 degree carbon atom. Next, in isobutyl chloride. What is isobutyl chloride? Let us write that. CH3, CH. This is your CH3 and CH2, Cl. Isobutyl means they said isopropyl chloride, isobutyl chloride. Okay, isobutyl chloride, what happened? Chlorine is attached to 2 hydrogen atoms. 2 hydrogen atoms means 1 degree, isn't it? Sorry. Third one, N-propyl chloride. 1, 2, 3. Here also your halogen atom is attached to 2 hydrogens, means it is also 1 degree. Yes, 1 degree. N-butyl chloride. The fourth one is what they asked. 1, 2, 3, 4. This is chlorine. Here also your chlorine is attached to 2 hydrogen atoms. So this is also 1 degree. Correct? So they asked what is 2 degree. Now the 2 degree part is isopropyl chloride. This is the answer. Easy. Elaborate the structures. So 2 degree means 1 hydrogen, 1 degree means 2 hydrogens. Easy. Next question. Which one of the following is not an allylic halide? Which one is not an allylic halide? Careful. Not. Draw the structures again. So they have given 4 bromo pentuene. 4 bromo pentuene. Let us write the structures. First of all, what is allylic means? What is allylic? I told you just now, isn't it? Careful. So concept is, they asked me what is not allylic. That is what I need to understand. Carefully draw the structures. One after the other we will draw. First one, 4 bromo pentuene. Okay, CH3, CH, CH, double bond CH, CH3, 4 bromo pentuene. Okay, now what is this hybridization? This is sp3. This is what? sp2. This is 1, 2, all single bonds only. No, so this is also sp3. Now here there is a double bond, so this is sp2. This is also sp2. This is sp3. Okay. Now allylic, as I said, as we have seen earlier, bromine is attached to sp3 hybridized atom next to sp2. Correct na? Yes. So this is allylic. We already studied. Allylic comes under sp3 hybridization. Vinylic and benzylic comes under sp2. Correct? So here bromine is attached to sp3 hybridized carbon. That means this is allylic in nature. Allylic means halogen attached to sp3 hybridized carbon. They asked me not, na? So ruled out. This is not. Next one. 3-bromo 2-methyl butanene. Okay, let us write 3-bromo butanene. Okay, here your CH3 is here and here your bromine is here. Correct, na? Alright, now check. Bromine is attached. Now what is this? This is sp3. Okay, what is this? This is your sp3 again, because all single bonds, sp3. This is your sp2. This is your sp2. Correct, na? This is also sp2. Okay, now tell me, bromine is attached to sp3 hybridized carbon atom. So this is also allylic in nature. You're able to see how I am writing. Okay, next one. Next one. I don't have place. Okay, I'll use the board here only. I should use 1-bromo 2-butene. CH3 CH double bond CH single bond CH2 Br. Now you see, bromine is attached to sp3 hybridized carbon. This is sp2. This is sp2 because double bond is there. This is sp3. Okay, this is also allylic only. Okay, now they said which is not allylic. Now you only tell me which is the only thing left. So first one gone, second one gone, this also gone, this is also gone, this also gone. All are allylic. They asked me to find out last one. This is the answer. Why? I'll show you. Not allylic compound. So 4-bromo butanene. Okay, 4-bromo butanene. Now let us see what is this hybridization. This bromine is attached to sp3. Okay, here also this is sp3. This also is sp3. This is sp2. Okay, here double bond. Here also your 2 hydrogens are there. sp3. Okay, now bromine is attached to carbon next to sp3. Correct? Just see here, bromine is attached to carbon next to here also sp3, here also sp3. Now in allylic, what is the concept? Adjacent to that there should be sp2 hybridized carbon. Correct, na? Adjacent to bromine there should be sp2 hybridized carbon. Adjacent to bromine there should be sp2 hybridized carbon. Correct. But in this case, bromine is attached to a carbon which is sp3. Oh, that's why this is it is not an allylic compound. Very carefully you should understand this, because suddenly you will find a difference. That's the reason you have to draw everything. So in allylic, the bromine whatever is there is attached, whatever it should be, adjacent one should be sp2, adjacent one should be sp2, adjacent one should be sp2, adjacent one should be sp2. But here in this case it is sp3. That's why it is not allylic. Easy, very easy. Shall I check whether it is recording or not? I'll check. In between, if you don't check, na, it will be a problem. It is recording. Alright, next question. Interesting. Let us go to the nomenclature without wasting time. Carefully we will understand one by one. So nomenclature, alright, careful. So first of all, in nomenclature rules, the main chain, selection of the main chain, that is very important. Correct, na? Selection of main chain is what is important, and numbering of halogen atoms, yes, or numbering of hydrocarbon. Same rule here also, same. Okay, so here selection of main chain and numbering of hydrocarbons. Okay, numbering of hydrocarbons. And here you should consider halogens as substituents. Consider halogens as substituents. Remember this, as substituents. Next important thing is, always remember the rule, number of carbons greater than maximum number of substituents, greater than lowest set of locands. I'll tell you what it is. Lowest set of locands greater than this is greater than alphabetical order. This is greater than, when I use a question you will understand, alphabetical order. This is the rule. Remember, this is the rule which you should follow. Okay, let us take one example and see so that you will understand it. Now this is one example, CH3, CH3, CH2, CH2Br. Now what did I say? You have to number it from the substituent. Yes, substituent, halogen substituents. Start numbering from wherever halogen is there. Start numbering, giving that as a first number, minimum number. So what is the name of this compound? This is 1-bromopropane. Easy, 1-bromopropane. Now let us see one more. 1, 2, 3, 4. And there is one alkyl group. How should you number? You have to number it from here. 1, 2, 3. What is this? This is called 1-chloro. Okay. 2-methyl propane. 1-chloro, 2-methyl propane. Easy? Easy. Something like that. Okay. Let us do one more question. 1, 2, 3 and 4. There are 2 methyl groups here. CH3, CH3. How do you name this compound? Start numbering from here. It is basically, now what you should do, as I said, the carbon which is adjacent to the halogen should have 1 first number. This is your numbering. So what does this look like? This is 1-chloro. Okay. Then you have your 2, 2. Between the numbers you have a comma. Then it is dimethyl propane. Dimethyl propane. Easy? Very easy. So what should I remember? I have to always number it from the halogen side. The halogen, whatever is there, from there that should get the minimum number. Shall we try one more question? One more? Yes. Now name this compound. This is there, this is there, this is also there, this is also there. Simple? Yes, same. 1-chloro, 2,2-dimethyl propane. Correct? Okay, so let us write 1-chloro. I think I have written already. Again, 2,2-dimethyl propane. This is easy. This is easy. Okay. Now something like that. Shall we do with one more? Like, let us change the position of the halogen atom. This is your halogen atom which I have shifted. From the starting I have shifted the halogen atom here. Okay. Now name this compound. It should get the minimum number. So 1, 2, 3, 4. Correct. Now what is this? This is 2-chloro. Okay. Second position, hyphen 3. There are 2 methyl groups. So now careful thing is, if I start from here 2-chloro, okay, if I start from here 3-chloro, but here we said the longest chain I need to check, I should give preference, no? So wrong. I need to start from here. 1, this is 2, this is 3, this is 4. So this becomes 3-chloro, 2, 2. This is 3-chloro, 2, 2 methyl butane. 3-chloro, 2, 2 methyl, because the longest chain is what is preferred. Correct na? Yes. Okay. Now once again let us take one more example with the aromatic ring. Suppose there is an aromatic ring like this. Okay. Now you have your bromine here, you have your bromine here. Now how should I number? This is 1, this is 2, this is 3, this is 4, this is 5, this is 6. IUPAC name 1,3 dibromobenzene. 1,3 dibromobenzene. Okay, this is okay. Now suppose there is one more question given like this. One with chlorine atom, one with nitro group. Now how should I number? Alphabetical order. C comes first, A, B, C, D. Second, third, 4, 5 and 6. What is this called? 2,4 dinitro chlorobenzene. 2,4 dinitro chlorobenzene. Easy. So this is your one, this is second one, this is third one, this is fourth one. Ma'am, still it is confusing. Shall we do some more? Yes, let us do some more and see so that it is easy for us. Now name this compound. CH2 double bond CH3 CH2Br. Okay, from where should I number this double bond? As I said, it is given more preference. This is 1, this is 2, this is 3. What is this? This is 3-bromo. First name the halogen, then 2-methyl propene. 2-methyl propene. 3 carbon atoms, so propene. Now shall we see this compound? CH double bond CH CH2Br. How should I number this? Double bond should get. Okay. Now careful when you are starting with this compound. If you start from here, bromine atom, first preference 1, 2, 3, 4. So what is this? This is 1 bromo, but 2 ene. That's all. Easy? Alright. Like that, it is very easy to name. Just same thing like, primary, secondary, neo. Shall we number it? Okay, we'll take some examples and understand it. Careful. Anything, if you get any confusion. Okay, further, let us do some more examples if you're getting confused. Now, if benzene is a substituent, if you think benzene is a substituent, let us take one benzene. Okay, let me take the next page. Suppose if benzene is a substituent in your reaction. Okay, benzene is substituent. Okay, no, I didn't understand, ma'am. I need to further, and we'll do some questions. So benzene, if it is a substituent, you will call it as phenyl. Careful. Okay, so let us write. There is one structure like this. Okay, now then with this you have CH2Cl. Now what is the correct name? What is the incorrect name? I'll tell you. Now chlorophenyl methane or chloromethyl benzene. Which one is correct? As I said, if benzene is a substituent, you should call it as phenyl. So chloromethyl benzene, this is wrong. Chlorophenyl methane is right in nature. So you have to use, if benzene ring is there, you have to use it as phenyl. Don't use it as benzene. Okay, careful. Okay, let us make one more. I am asking you to write the structure of 2-chlorophenyl. Okay, 2-chlorophenyl, 1 iodo-octane. Okay, shall we try this and see? Okay, what did they ask me? They've asked me to draw the structure. Okay, so what is this? First thing is iodo-octane. Octane means how many carbons are? 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 iodines are there. 8 carbons are there. Now, they said in the first carbon atom, iodine is there. Okay. Then fill in all the hydrogens which are there here. All the hydrogens which are there. All the hydrogens you are filling in. Okay. Then this is CH3. Now, say in the second carbon, now numbering to start from here. 1, 2, 3, 4, 5, 6, 7, 8. 1 is over. Now in the second carbon you have, now careful, there is one benzene ring in the second carbon, so I should not put 2. In the second carbon there is phenyl group, and that phenyl group has chlorine in the second position. 1, 2, 3, 4, 5, 6. Now careful, everything is over. Now let us check. 2 okay, in the second position 2 chlorophenyl and 1 iodo-octane. Perfect. This is easy, very easy question. So simple. Now let us start with the questions and understand this. Okay, let us start with the question now. Careful. See this question. This is one of the hot question, very important. Just see. Match the isomers given in the column 1 with their names given in the column 2 and mark the appropriate choice. Okay, now I have to mark. Now just check carefully. There's one more question. Okay, one more question. Let us take this here only. Now A, Let us take A is related to what, B is related to what, C is related to what, D is related to what. Let us check this and understand. A compound, bromine, is here. From where should I name the, I should start with this 1, 2, this is 3, this is 4, this is 5. So where is this? 2-bromopentane. So A is related to 2 option. Correct. Then B part. I have to start numbering from where? From here. This is 1, first carbon, first 1 bromo, 2, 3, 4. There is methyl group here. So 1 bromo, 3 methyl, 4 carbons, butane. So option 3 is this. Easy. 2 and 3. Next compound. I have to again start numbering from this. Carbon 1, carbon 2, carbon 3, carbon 4. So what is this compound now? 1 bromo, 2 methyl butane. This is related to option 4. Now D part, this is left only na. So 1, this is 2, this is 2, this is 3, this is 4. 2 bromo, 3 methyl butane. This is related to option 1. Easy, very easy question. So A related to B3, C4 and D1. Easy question. Okay, let us solve little more questions. Give the IUPAC name of the following. Alphabetical order, careful, you have A, B, C, D in A, B, C all. So bromine, chlorine, careful. Always remember, you should give according to the alphabetical order. And then bromine comes first because here 2 bromines are there as a substituents. That's why we start with taking as 1 chloro. Okay, 1 chloro. 2 are there. 2, this is 1, this is 2, this is 3. 1, 2, 3, 4 and 5. Pentane chain. 1 chloro, 2, 3 dibromo, all small letters, methyl. Which methyl? 2 methyl. 2 methyl. 2 is there, 2 here. 2 methyl. 2 methyl pentane. Correct na? So 1 chloro, 2, 3 dibromo, 2 methyl pentane. So careful, this is very important question. Whenever you have 2 substituents, take it as 2 different positions. One more question. Dot the structure of 4 bromo, 3 methyl pentatoene. Easy. What did they ask me? 4 bromo, 3 methyl pentatoene. Okay, first I'll make pent. 1, 2, 3, 4 and okay. Ene. Okay. So pent. First they said 4 bromo. First carbon, second carbon, third carbon, fourth carbon, fifth carbon. So I am making 4 bromo. Okay. Third position I am making your methyl. Methyl is okay. Methyl. Pentatoene. Pentatoene. Perfect. Yes. So even if you don't mention this also, like this also will do. Like this also it will do. That also will do. You can leave it like this. Not a problem. Okay. Chalo. Yes. Next question. Very important. A compound is formed by substitution of 2 chlorine for 2 hydrogens in propane. The number of possible isomeric compounds. This is NCERT page. Okay. Alright. So let us see. They said a compound is formed by substitution of 2 chlorine for 2 hydrogens in propane. Let us take your propane. Okay. Let us take your propane. This is your propane. Correct na? Yes. So what did they do? They've added 2 chlorine atoms. They've removed hydrogen atoms. 2. So now I'll add 2 chlorine atoms to this propane. Okay. I'll open up the chain. This I'm adding. This is your propane chain. Na? I'm adding 2 chlorines to this. Chlorine, chlorine. What is this? This is called 1,1 dichloro propane. Okay. Now next, what did we add? We've added 2 chlorines, different position. 1 chlorine here, 1 chlorine here. So possible isomers I'm writing 1,2 dichloropropane. Okay, dichloropropane. Next, plus. I am taking propane, I am adding here to the center. 2,2 dichloropropane plus 1,3 dichloropropane. Easy? Easy. These are all the 4 substituents or formed by substitution of 2 chlorine atoms for 2 hydrogens. I added 2, I removed 2 hydrogens. That's all. These are all the 4 possible things. Let us see next question. The IUPAC name of this compound. Okay, I don't know what is this. Let me elaborate the structure and then understand. Okay, first of all, there are 3 methyl group systems. 1 methyl group, okay. Second methyl group, okay. Third methyl group, okay. This is your carbon and 1 chlorine. Oh, such a easy question. Yes. Now name it, because you have to see the substituent as well as you have to see the parent chain atom also. Correct na? Now this is your chain. Okay, this is the longest chain, prop. So I'll take this as the longest chain. This one, the straight chain. This one I'll take it as the longest chain. So I'll name it as 2 chloro. This is 1, this is 2, this is 3. Okay, 2 chloro, 2 methyl propane. Easy? Easy. 2 chloro, 2 methyl propane. Easy? Easy. Yes. Now next question. Okay. IUPAC name of this compound. Oh, nothing. Write the structure down. Write the structure like this. First write the structure like this. Okay. Now you are going to number it. This will get minimum number. Then comes this carbon. Then comes this carbon. Then comes this carbon. Now name it. 2 bromo. Where is 2 bromo? Okay, 2 bromo. All right. Then let us write 2 bromo, 1 chloro, butene, 1 chlorobutene, or 1 butene, 1 chloro, 1 butene. So option 1 is correct. Easy? Okay, easy. Nothing. Numbering only is important. Next question. Phosgene is a common name for what? Phosgene is nothing but phosgene. Formula is phosgene. Formula is COCl2. Okay, that's nothing but carbonyl chloride. Carbonyl chloride is phosgene. Little bit no problem. Nature of CX bond. Okay, so CX bond nature. Careful. Let us understand the nature of CX bond. First of all, in nature of CX bond, what you should understand is, careful, just check. Here halogen is negative, electronegative. So because of this electronegative halogen atom, it tries to drag the electron density towards itself. So when it drags the electron density, because of its electronegativity, it will become partially negative. This becomes partially positive. Correct? Yes, because of the electronegative. That's why, because of the electronegative nature, CX bond, I'm sorry students, bond is polar. Because there are 2 poles. Correct? Yes. This is first point. Second point, what you should remember is, based on the size of halogen atom. Size of halogen, careful, the electronegativity, that also varies based on the halogen. Fluorine is most highly electronegative, but size of the halogen atom, based on that also different physical properties will change. Yeah? Yes, I'll tell you how it is. Now carbon halogen bond length, CX bond length also matters because of this. Careful, CI bond more than CBr, more than CCl, more than CF. Okay, there is a bond in between all and reduce. Next point to remember is, careful, bond length of CX bond is directly related to, what is that? Careful, not directly, basically inversely related, I have to tell you, inversely related to bond enthalpies. Ma'am, what is this? When we do the questions, you will understand. Yes, bond length, and most important, next, bond enthalpy. Bond enthalpy, just note it, I'll show you where to apply. CF greater than CCl greater than CBr greater than Ci. Okay, next, order of dipole moment. Order of dipole moment is, do I have place in the next thing? Okay, here only I'll write. I don't think I have place. I have a question, so I have to write order of dipole moment CH3Cl greater than CH3F greater than CH3Br greater than CH3I. Okay, yes, so just remember these points and this will help you in solving the questions. First question, such a big question which is there in page number 312. The main difference in CX bond of haloalkane and haloarene is what? Okay, the main difference they're asking. Simple, let us read. Haloalkanes are less reactive than haloarenes due to difficulty in breaking CX bond. Okay, what is the main difference they're asking? In haloalkanes, C is attached to sp3 and haloarenes it is sp2. Okay, CX bond in haloalkanes is shorter than haloarenes. CX bond acquires a double bond character due to higher electronegativity of X than nothing. Simple. The main difference of CX bond in haloalkanes and haloarenes, remember in mind, only one mind. Based on hybridization. In chlorobenzene or haloarene, it is your sp2 hybridized carbon atom. In case of your haloalkane, it is nothing but, anything it may take, it is nothing but single bonds sp3. So always the only difference between both of them is based on their hybridization. Don't think about anything, just blankly write, go and tick the option B. That's the only difference which creates the magic. Okay, next question. CCl bond of chlorobenzene in comparison to CCl bond in methyl chloridase. This is there in NCERT page number 312. CCl bond in chlorobenzene. I just now said na, think in terms of hybridization, double bond or single bond. That's all. The whole concept is clear. First concept is CCl bond in chlorobenzene, C6H5Cl. And CCl bond in CH3Cl. You tell me, in C6H5Cl, what is there? sp2 hybridization. S character is more in this. So, what will happen to the bond? Here, there is a double bond. Here, there are all single bonds. Now, here the CCl bond of chlorobenzene in compared to this one is what? Double bonded, is close, S character is more, very close. So what will happen? It is close means the bond is short and the bond is strong. Correct na? Yes. Why? In this one there is a concept of resonance. In this there is no resonance at all. So CCl bond of chlorobenzene in is nothing but shorter and stronger because of what concept? Because of resonance. Easy? Easy. Next question. Now let us see the methods of preparation of your haloalkanes. Nature of CX bond, those are asked. Gradually when we do physical properties, you'll see more questions. So in preparations of haloalkanes, careful. So basically haloalkanes are prepared from, first one is from alcohols. correct na, from alcohols. So alcohols, there are a lot of questions based on chirality, based on chemical properties. We'll do all those. So from alcohols I will try to make one flow chart here only, so that it is easy for you to understand. First of all, alcohol Lucas reagent test. This is the reagent. You will be getting alkyl halide plus water. Lucas test. This is Lucas test. Then careful, you will be using HBr in the presence of ZnCl2 to get your RBr, alkyl halide, that is bromoalkane, alkyl bromide in that terms. This. If you want to get your Ri, you have to use Hi. Careful. If you want to get from alcohols, somebody is asking to prepare alkyl bromide, you can also use NaBr plus sulfuric acid. Okay, and this happens in terms of HBr, hydrobromic acid. If somebody is asking you to prepare your RCl, you can also use PCl3. The byproducts are H3PO3. If you are trying to prepare PBr3, you are using PBr3, then you will be getting RBr, then H3PO3. If you are taking alcohol, if you are using red phosphorus and you are using bromine, then you can prepare RBr. Same red phosphorus, if you are trying to use with iodine, you will be getting Ri. And most economical method of everything rather to do get is economical method, and common thing is SOCl2, thionyl chloride, SOCl2, where you will get RCl and you will be getting gaseous products. Here your alkyl halide is the purest form, most economical and cheapest one to prepare. Got it? Yes. Now most important thing and question to remember here is this method used to prepare aryl halides, or is this possible? Careful, this method, whatever SOCl2 method, is not used to prepare, it is not used to prepare from alcohol. If you are using SOCl2, you will not get this halide. Reason, because here in this case there is a partial double bond character, and breaking of this bond is tough because of resonance, because of resonance there is a double bond which is formed, so breaking of the bond is tough. So you write because of resonance bond breaking is tough. That is what you are going to tell. Okay. Next, preparations are over. No, preparations are there from hydrocarbons, right? The second preparation after alcohols is from hydrocarbons. Okay, from hydrocarbons what you have? Yes, hydrocarbons only means it is free radical halogenation. Correct. Now what is free radical halogenation reaction? You are going to take methane, you will add chlorine, and you will do this reaction in the presence of sunlight. So one hydrogen atom will be replaced with halogen atom. Correct na? Right? Same. If you take propane also, if you take ethane also, same thing. Same. One hydrogen atom will be replaced with one halogen atom. Same. So like that, whatever you are taking, one hydrogen will be replaced. Suppose if you take prop, and just take this. Here chlorine you're using ultraviolet light. In this, what will happen? You will be getting different isomers. So first time your halogen atom will be last, means it will be occupying the first position. Later you will be using that halogen atom in the second. Like that you will be getting possible isomers. So when you are using more than two, you will be getting different compounds like mono, you will be getting dihalogen compounds, you will be getting polyhalogen compounds, all you will be getting using this. Easy? Yes. Same thing, suppose if you are using an aromatic ring CH3, you are using bromine, you are heating it, so you will be getting halogenation, one more halogen, 1 will be replaced with HBr. Simple, easy. So free radical halogenation, I'll show you how questions are asked. Next, suppose if they ask you a question, write possible structural isomers of CH3 taken twice, CH, CH2, CH3. This is what they asked. So how should you write this? See this. First you open the chain. 1, 2, 3. Okay. This is one hydrogen. This is one more hydrogen. This is one more hydrogen. There are CH3. This is CH3. Correct now? So first one. What will I do? First hydrogen, possible structure isomers, they write possible structure like monochloro, find, right? Right? Possible monochloro structure isomers. They want us to substitute chlorine into this. So first start from here. CH3, CH3, CH, CH2, CH2Cl. This is first one. Second one. Slowly get that into second carbon. Now third one. Get that into third carbon here. Then last one, you get this into the fourth carbon. Reduce one. That's all. Simple. These are the possible isomers. Easy, very easy. So gradually understanding the concept. Now after the monohalogen compounds reactions, next one you have my electrophilic substitution reactions. This is one more preparation, the third preparation after your alcohol. After that, after your free radical halogenation, next one is electrophilic substitution reactions. Okay, now first I am taking toluene. Okay, then I am using Fe plus Cl2. So what will happen? I will be getting two different compounds. One with your chlorine, then one more with your. Okay, so orthochlorotoluene, parachlorotoluene. Correct na? Orthochlorotoluene, parachlorotoluene. The same thing you can also use by Cl2 plus FeCl3. FeCl3. So what is this? Orthochlorotoluene. This is opposite direction, na? Parachlorotoluene. Right? So orthochlorotoluene, paratoluene. You can use the same. Suppose if I am using bromine, if it is here or here, not a problem. Fe plus Br2. Same thing, FeBr3 plus Br2. What will I get? I will be getting bromine. Here I will be getting This is ortho-bromotoluene. This is para-bromotoluene. Correct, na? This is bromine. Suppose if they ask you to prepare HI, this is important. I am taking benzene, iodine. This is a reversible reaction. This is with AlCl3. What will you get? I will be getting iodo plus HI. Now here what happens? This is HI is a reducing agent, and you are adding one oxidizing agent like HNO3 and H2SO, HI4, not H2SO4, HI4. What will happen? You will get iodine back. That's the reason. These reactions are reversible. Reactions of iodine are reversible in nature. Reversible. That's why it will require an oxidizing agent. Because this reaction requires presence of oxidizing agent to oxidize HI to further iodine. Okay. So you need to remember HI is required to release or convert into iodine. Now you know chlorine we prepared bromine, we prepared iodine. But in case of fluorine, what will happen? There's high reactivity of fluorine, right? There will be an explosion. That's why fluorine compounds are not prepared by this method. Remember, fluoro compounds are not prepared by this method because of its high electronegativity and it will explode. Got it? Explode? Yes. So next reaction, what is next reaction? One second, let me check. I'll just take a small pause. One pause. All right. Now welcome back. Now we have done the preparations of using we are getting from alcohols. We have got different varieties of alkyl halides. Then we have got by electrophilic substitution reactions also we did. Then we also took the concept of free radical halogenation. Now the next variety of preparation, that is which you are studying for both the haloalkanes and haloarenes. Next is a Sandmeyer's reaction. Okay. In Sandmeyer's reaction, very famous reaction, name reaction for your boards, easy also. Let us make. So basically Sandmeyer's reaction is used to convert primary aromatic amine. So remember like this, Sandmeyer's is used to convert primary aromatic amine to diazonium salts. Diazonium salts. So this primary aromatic amine to diazonium salts, let me check whether it is recording again. I should check, because suddenly if it disappears, it's waste of content. Okay. So how you're converting? You're converting primary aromatic amine using your HCl and NaNO2. Okay. So here you are taking your aniline or primary amine, that is your aniline. What you are doing, you are using this reagent HCl and NaNO2. So this NaNO2 when you are using, it's going to convert it to diazonium salts, that is BDC, that is benzene diazonium chloride. Let us write this, benzene diazonium chloride. So benzene diazonium chloride, once you know, what is important is further products what are formed, because this is used as a base for many conversions. Suppose benzene diazonium chloride, if I am using Cu2Cl2, I will be getting chlorobenzene. This is one type of product which we get. Suppose same thing, diazonium chloride, if I am using Cu2Br2, I am getting bromobenzene. This is one variety. If I am using potassium iodide, I will be getting iodobenzene. This is one type of conversion. If I am using this diazonium salt for lot of products. So this is the base for everything rather. That's why Sandmeyer's reaction, conversion of primary aromatic amine to diazonium salts is important thing. Next variety of reaction is you are trying to get your alkyl halide from alkenes. Remember that. Okay, my writing pad got disconnected. So 1 second, please. Sorry. Okay. So the next type of preparation, that is the D part, is from alkenes. So till now what did we learn? We have learned by free radical halogenation, Sandmeyer's reaction, then from alcohols, and now this is from alkenes. So basically alkenes, nothing you are trying to add. It is just the addition of hydrogen halides. That is, you'll either add HCl or you'll add HBr or you will add HI or you will add HF. Let us see how we are adding this. Conditions are what? Suppose if you have a symmetrical alkene like this, you are adding HCl to this. It is equal, the bond breaks and you will add, there is no problem. You can directly add it as it is in this way. There is no problem. Problem all starts when there is an unsymmetrical alkene in this way. Unsymmetrical alkene. Here there are 2 carbons, here there is 1 carbon. Suppose if you are adding HBr to this. Here H is positive, bromine is negative. Now careful. In this case, there are 2 varieties of products formed. That is, if the positive part, the positive addendum, careful, if it adds to the carbon, see here simple, let me write the product, then you will understand. CH3, CH, CH2, one product is bromine, this one, and one more product is CH3, CH, H and Br. Now check carefully. Now in this case, this is Markovnikov addition. Markovnikov, Ni, Markovnikovs, COVS. This is anti-Mark addition. Anti-Mark. Now observe carefully. In this case, the positive adds to the carbon which has positive, adds to carbon atom which has more number of hydrogens. More number of hydrogens. This is easy. Now what is this? Careful. Hydrogen, talk in terms of hydrogen, you will remember. Hydrogen adds to the carbon having more number of hydrogens. This is Mark. Hydrogen is adding to a carbon having less number of hydrogens. This is in the form of peroxide, that we will see. In Mark, hydrogen adds to carbon having more number of hydrogens. Remember this, it is easy for you. Okay. Yes. Now let us see one more. Suppose there is one ring in this way. You have hydrogen. In this case, there is double bond, there is hydrogen and there is hydrogen. Now you are adding HBr to this. H plus and Br minus. Now hydrogen should add to the carbon having, now how many hydrogens are there here? 1 hydrogen. Here how many hydrogens are there? 2 hydrogens. So hydrogen should add to the carbon having more number of hydrogens. So what is the major product here? Benzene ring. Your CH is here, negative part, and your CH2 and H. So this is your major product. So in Markovnikov addition, hydrogen adds to the carbon having more number of hydrogens. Easy? Easy. Now this is Mark addition. Now what is anti-Markovnikov addition? Anti-Mark addition happens in the presence of peroxide. Correct? This should happen in the presence of peroxide. Here only we are adding addition of HBr. Only addition of HBr will happen here in this case. Careful. Now I have a benzene ring. I have a compound which has double bond like this. Here how many hydrogens? 1 hydrogen. Here how many hydrogens? 2 hydrogens. Now careful. H plus Br minus in the presence of peroxide. Negative addendum, nothing, simple. Careful, remember, think in terms of hydrogen plus. That's better. Either you think in terms of negative or the positive, either ways. Now, in earlier case, hydrogen added to the carbon having more number of hydrogens. Here, hydrogen will add to the carbon having less number of hydrogens. Less. So, bromine goes and adds here. So, what do I get? I get CH2, CH2, CH2Br. So, simple now. So, in this mark, more number of hydrogens. In anti-mark, less number of hydrogens. Only Br. Easy. Now, the last, I think one more preparation is there. Addition of halogens. I can directly add halogens using either, chlorine or bromine by this particular thing. That is, if you are taking any alkene, if you are trying to use bromine in carbon tetrachloride, to directly break and you can get a compound. This is one variety. And last but not the least, there is two more name reactions. That is Finkelstein reaction is one, and one more is Schwarz reaction. These two are called halogen exchange reactions. These two are called halogen exchange reactions. In Finkelstein reaction, what are you preparing? Basically, you're preparing iodoalkanes. Take one chloroalkane. You're trying to introduce sodium iodide and acetone. I will replace your Cl. You will be getting iodoalkanes. Okay, and NaCl precipitates out. In Schwarz reaction, you are preparing fluoroalkenes. So for this, here you took chloro, here you took bro. So what will you do? You have to prepare fluoro. So you will be using silver fluoride. You will be using Hg2F2. You will be using SbF3. So you will get fluoro AgBr, whichever one. AgBr will precipitate. It comes out as a precipitator. So here there is one point which you should remember. In water, AgF, why we are taking AgF? Because AgF is soluble. AgF is soluble in water. That's why we take this, soluble in water. If they ask you, remember this. We will not take AgCl or AgBr. So AgF is soluble. That's why we get this. And AgCl and AgBr are not soluble. Okay. That's the reason we take this and AgBr precipitates out. Okay. Now, in this case, if they ask you, why NaI, why not NaCl and NaBr? Same concept. Sodium iodide is soluble, but NaCl and NaBr are not. Will you remember? Yes. In first case, NaI is soluble, NaBr and NaCl are not. In second case, AgF is soluble, but not AgCl or AgBr. Got it? All the preparations. Now let us do the question now. All the preparations are over. So we did from alcohols, we did free radical halogenation, we did, from your halogen exchange, we did addition, direct addition, all those. Now let us do halogenation of alkenes is what type of reaction? Oh, halogenation. So halogenation, what did we do? We took an hydrocarbon, we added chlorine, we added in the presence of ultraviolet light, and one chlorine replaced this and we get HX or HCl. Correct now? So here what is happening? You are just adding chlorine. You are just adding one after the other. But is there any addition reaction here? No. We don't have addition. I should understand in terms of this. First of all, in this case, the chlorine oxidation number is 0. Here, the chlorine oxidation number is -1. So what is happening from 0? It is going to -1. It is decreasing. The oxidation number is decreasing. Correct, na? Decrease in oxidation number. What is it? Yes. Yes. Decrease in oxidation number is nothing but oxidative process. Increase in oxidation number reductive. Decrease in oxidation number is oxidative process. Correct na? So careful. You see? So endothermal, there is no heat. Isothermal, nothing. It is only oxidative or reductive. So halogenation is an oxidative process. Next question. Ethylene dichloride can be prepared by adding HCl2. Ethylene dichloride. They've given all options. Let us try one after the other. Ethane. CH3, CH3, HCl. There is no reaction with this. Remember. Next, ethylene. CH2, double bond, CH2 plus HCl. It directly adds. It will break the bond. Hydrogen goes and adds here. Chlorine here. CH2, CH3, CH2, Cl. This is which reaction? Addition reaction. Third, acetylene itself. I will take acetylene here. I will add HCl to this. So what will happen when you add acetylene? Hydrogen here, chlorine. But there is a double bond here. Still there is a double bond. Further you add HCl to this. What do you get? You get Cl, and because you are adding the chlorine, so this will become ethylidene chloride. It is called ethylidene chloride. What is it called? Ethylidene chloride. Okay. It further you are adding HCl. So this chlorine is here only. One more chlorine comes and adds. It is called ethylene chloride. So now last one, ethylene glycol. Ethylene glycol has 2 OH groups. You are adding, because 2 OH groups means I will add 2 HCls. What will it do? It will go and add to this. So now the name of this compound is ethylene dichloride. This is ethylene dichloride. Now see the options. Ethylene dichloride can be prepared by adding HCl to ethane, wrong. Ethylene, wrong. Acetylene, wrong. The answer is ethylene glycol. That means to get this, you should take ethylene glycol. This is the correct answer. Next question. The best method for conversion of an alcohol into alkyl chloride is by treating the alcohol with what? Conversion of alcohol to alkyl. I told you, the most economical method is SOCl2. Correct? Simple, because all are gaseous products. When you add to this in the presence of pyridine, all the chlorine replaces this, you get all gaseous products only. That's the reason we prefer this. So SO2 and HCl will leave and you'll get a pure alkyl halide. So that's the most economical method. Next question. Okay. Conat-Finkelstein reaction is used for the preparation of alkyl iodide. So we know alkyl iodide is what I am preparing using acetone. So what it is based upon, which fact they are asking. Sodium iodide is soluble in methanol while sodium chloride is insoluble in methanol. So I told you earlier this concept. Yes. So sodium iodide is soluble in methanol. Okay. Sodium iodide is soluble in methanol and NaCl is insoluble. This is the question. It's correct now. This is what I told. Remember the option 2 which I showed in the video. When I take Rx, when I am adding NaI and I am adding acetone to this NaI is soluble. Careful. It is soluble in methanol. Okay. Remember this. And you get Ri plus NaX. This what happens, this is insoluble. This NaX, whatever you are getting, it is insoluble in methanol. Okay. Me2CO. Okay. So where X is equal to, this X is equal to, it is either chlorine or bromine. That's why the correct reason is insoluble in methanol. So we are using NaI, we are not using NaCl or NaBr. Careful. Next question. Methyl alcohol reacts with thionyl chloride in the presence of pyridine. Okay, methyl alcohol reacts with, let us write what they say. Ethyl alcohol, okay, reacts with thionyl chloride in the presence of pyridine. Easy question, correct? To give what? Easy. OH is replaced. CH3, CH2, Cl plus SO2 gas plus high HCl gas, vapors. So the correct option is C. Correct now? Okay. Next question. The hydrocarbon, this hydrocarbon is given tertiary, undergoes reaction with bromine and chlorine in the presence of sunlight. If the reaction with chlorine is highly reactive and that of bromine is highly selective, so number of possible products formed, okay, number of possible products formed will be what? Okay, so let us take both conditions. I'll take first with chlorine. Okay, first I am expanding this compound. This compound is here. I am expanding it. Okay, hydrogen. Now it undergoes reaction with bromine and chlorine, both in the presence of sunlight. Okay, in the presence of sunlight means it shows substitution of one hydrogen atom, right? So first one I'll be getting CH3, one more CH3, one Cl. This one, correct? Next, one more. One is minor. This is minor product because it didn't substitute any hydrogen. In the second case, CH2Cl, then CH3, and this is your H. This is major product. Major. Let us take bromine. Again, same three compounds. Bromine. They said highly selective. They said highly selective. Again, same. In this case, as you got CC, CH3. This is Br. This is CH3. This is major. This is selective. In the second case, wherever you are getting the chlorine atom, you will be getting bromine there because they said selective. This is minor. This is minor. This is minor. Now, what is the question? What are the different products? Okay. So, chlorine being highly reactive, it will react with all types of hydrogen. Correct? Now, whatever hydrogens are there, it will react here. It will react here. Now, bromine being highly selective, it will react with only that hydrogen, which gives highly stable tertiary alkyl halide. Once again, I am writing what I said. First, chlorine is highly reactive, they said. So, when it is highly reactive, what does it do? It will react with all types of hydrogens. Correct? Now, available. Now, they said bromine is highly selective, they said. So, what will happen? It will react with only that carbon. Okay? It will react with that hydrogen rather, not carbon. Only with that hydrogen. What will happen? Where when it breaks, it has to release a tertiary alkyl halide. Tertiary alkyl halide means most stable, isn't it? Tertiary alkyl halide. So, this tertiary alkyl halide is most stable. So, it forms only one product. Only one product. So, whichever is tertiary alkyl halide, now you check, go back. This is tertiary alkyl. When it breaks, it forms tertiary alkyl halide. Na? So, with this product. Now, you tell me what answer. Where do you have the answer? Yes. This one, see here. Two products and one. This is for bromine. This is for chlorine. So, the correct option is option B. Because they said here, they said highly reactive, it can replace all types of hydrogens. All types. We can't write 3 because it is the same. So, here it is 2 up and this one, here it is only 1. So, option is 2 and 1. Easy? Easy. Next question. Oh, preparations of haloarenes. So, early we have come. Alright, let us see the preparations of haloarenes. Basically, careful. So, in preparations of haloarenes, nothing. I can prepare haloarenes first from arenes, from benzene or arenes. So, let us write from benzene. So, how do I prepare? I am going to take one benzene ring. Okay. I will add chlorine. I will use iron in dark. This chlorine goes and replaces this. I get H by Cl. Easy. Okay. Next, Sandmeyer's reaction is one more. Sandmeyer's reaction. Nothing. I can easily take 1 BDC, C6H5N2Cl. I will add Cu2Cl2 and HCl. What do I get? I'll be getting Cl plus N2 gas. Over. Third one, name reaction, Gattermann reaction. Gattermann reaction. In Gattermann reaction, again you taking BDC. In this you are adding Cu by HCl. You will get H5Cl plus N2. Correct? Only reagents are different. Last, Huns-Dicker reaction. Huns, Huns, DIEC, Huns-Dicker. Huns-Dicker reaction. DICKER. In Huns-Dicker, what are you doing? You're trying to use this plus you're using bromine in the presence of carbon tetrachloride, reflux, and the products formed is bromobenzene plus carbon dioxide plus silver bromide. That's all. That's all. These are the preparations. This is how you are preparing your haloarenes. Okay, you're preparing your haloarenes. So careful. Let us see one question based on this. In the preparation of chlorobenzene from aniline, the most suitable reagent is chlorobenzene from aniline, it seems. Okay, chlorobenzene. I am preparing from aniline. Okay, aniline. Alright. So, first aniline always convert it to BDC. That is the easiest way. Diazotization reaction. Diazotization reaction ZA. Diazotization reaction I can use HCl. So, convert this to BDC. Once you convert this to BDC, N2Cl, easy. You introduce Cu2Cl2. This is Sandmeyer's reaction. That is diazotization. This is Sandmeyer's. That's all. Over. So, which is the option? Correct option. And nitrous acid followed by Cu2Cl. Easy. Next question. Aryl halides cannot be prepared by reaction of aryl alcohols with PCl3, PCl5 or SOCl2 because aryl halides cannot be prepared by reaction of aryl alcohols with PCl3. Okay. We can't use it as we did it for normal alkyl halides. Why? Problem here is in aryl halides. Careful. Suppose if I take this OH. Okay. Now I am using PCl3. Simply I can replace this. I get RCl plus H3PO3. Here there is no double bond, no resonance, no double bond, no resonance, no problem at all. But in case of your alcohol, what will happen? Here, between the carbon-oxygen bond, here there is carbon oxygen. When you break this, there is a shift of bond, it will have partial double bond character. When it breaks, this bond shifts, you have partial double bond character. Double bond character. This partial double bond character, here it is single bond. Now which is easy to break? Single bond. This is very difficult. Partial double bond is very strong, correct? Huh? Double bond is more stronger than single bond. That's why, that's the reason we have answer. Phenols are highly stable compound. That's not the reason. Carbon oxygen bond in phenols has partial double bond. This is the valid reason. Very closer. This is not the valid reason. This is not the valid reason. So double bond is stronger than single bond. Easy. Next question. Oh, this is very interesting question. Which of the following is the best method for synthesis of 1-bromo-3-chlorobenzene? They've given me option A, option B, option C. Okay, let us try. Sorry, physical properties. No, let us try this. I should synthesize what? 1-bromo-3-chlorobenzene. I have to synthesize. First I'll make the answer. What should I synthesize? I have to synthesize 1 bromo, 3 chloro. Okay. So what are the starting materials here? In this case, bromo. Here already this in this option A, already 1 bromo is there. Okay. In this case, nitro. Okay. Next case, chloro. Okay. So first of all, carefully understand one clue for you to get. I want 1 bromo, 1 chloro. Na? See here. You see the reagents. Here sulfuric acid means the final product you'll be getting SO3H, addition of electrophile. This I can't use. In this case, there is a bromine. I can use this because last product I need bromo. In this case also there is bromine. I can use this. Okay. Now go back. There is HNO2 here, nitrous acid. Good. If I have nitrous acid, I can get BDC. If BDC is there, it is easy for me to get. But in this case also, HNO3 is there. Here also I can get BDC. Oh, this also I can use. Go back. In this case, zinc. Are both the options? No, okay, different. Here, zinc and HCl. Reduction, correct na? Reduction, addition of hydrogen, zinc and HCl. Okay. Now, in this case also, zinc and HCl. Oh, here also a reduction I can do, addition of hydrogen. Here also zinc, addition of hydrogen, reduction I can do. Both are same. Oh, here Cl2, AlCl3. Okay, this reagent is your alkylation. Correct na? It can add chlorine to this ring. In this case, this is the difference. This is sulfonation. Okay, it will add SO3H. So I can't use this at all. This is ruled out because I want chlorine component, chlorine atom. Here I can use. So this is a perfect match for us. So shall we start? This is how you should analyze. Now see here. I took option B is correct. I took nitro. Okay, first NO2. Then what did I do? I added chlorine and AlCl3. What will happen? AlCl3 is an electrophile. It will go and add the electrophile chlorine. I am adding zinc and HCl. Removal of oxygen, addition of hydrogen. NO2 will become NH2. Chlorine is there only. Sorry, I added HONO, nitrous acid. Cold conditions, I get BDC, N2Cl and your chlorine. Now, what did I do to this chlorine? I have added Cu2Br2. That's all. Over. Nitrogen gas is out. So the option B is correct. Easy? Very easy. Next question, physical properties. We'll take a short break here and then we'll join again. Alright, now let's start with the next topic. That's nothing but your physical properties. Alright, students. So in basically physical properties, there are certain questions which we need to concentrate. The topic is easy, but there are certain points which I'm going to tell you and we'll apply these topics in the questions. Let's write. First, in the physical properties, okay, let me take a red pen so that it is easy for you all. Okay, alright. So in physical properties, first important thing, let's talk about boiling point and melting point. Boiling point and melting point. Okay. So in boiling point and melting point, what is important? Basically, molecules of organic halogen compounds. So what did we learn? Here in haloalkanes and haloarenes, there is difference in electronegativity, correct na? Between CX bond, one is partially positive in nature, one is partially negative in nature. So because of this, what happens? There exists a concept called polarity. Alright. This concept of polarity is always there working between both. Now, because of this, the dipole as well as van der Waals forces of attraction are very high, very strong in halogen derivatives. So what important is, higher the or higher or greater letters, right? Greater the polarity between formation of two poles because of electronegativity difference. Yes. And next important thing, higher the molecular mass of hydrocarbons, higher the molecular weight or molecular mass of hydrocarbons. Hydrocarbons here, this is your alkyl group. HC means hydrocarbons. Yes, so what will happen because of this concept, there are two things which works. One is dipole interactions as well as and van der Waals forces of attraction. Van der Waals forces of attraction. These two are important things. They are very, very strong. They are stronger in halogen derivatives. Stronger in halogen derivatives. So careful. Halogen derivatives, this is the thing. So careful and remember these points. Okay, right. For example, if I take two things. Okay, halogen derivative and parent hydrocarbon. Now see here. Now there is one compound like this. Now this compound, there is one halogen atom, bromine. And there is one more compound in this way. So both, see how many carbons are there? 1, 2, 3, 4. Correct, na? Right? Now I'm drawing one more hydrocarbon chain. 1, 2, 3 and 4. 4 carbons. So you tell me in both of them which will have more boiling point. Correct? So in this case, in boiling point trend, this will have more boiling point because the halogen atom is also added along with the hydrocarbon chain. Correct, na? Suppose if I take for only given alkyl group, I'm talking only about alkyl group. Only alkyl group is there. So what will happen to the boiling point trend in this case? Here alkyl halide, iodine is bigger, then bromine, then RCl, then RF. Am I right, students? Yes, because the size of the halogen atom is big enough. This is one point which you should remember during your exam. Next important thing is boiling point is inversely related to branching. So one inversely related branching. For example, what does this concept mean? That means before I go to this question, I don't have place. So I'll just write here only. Boiling point is inversely related to branching means if I have to take, just see here. So here, see here, 1, 2, 3 bromine. Okay, this boiling point is more than one bromine here, then your just in this way bromine. Now see here, what are you observing? This is carbon, this is carbon, this is carbon, this is carbon. Now observe. In this case, the surface area is more. Okay, the surface area is more. Now what do they say? If the branching is decreasing, boiling point increases. Okay, once again, if branching is decreasing, boiling point increases because the surface area is more. That means here branching is less. So it is expanded. So the surface area is more means I require a lot of boiling to break the bond. So once again, as the surface area increases or the branching decreases, boiling point increases. Is it okay? Is it okay? Easy. Same thing, I will write one more concept, what is melting point. So remember, for this, the surface area is more, surface area is less. That's why wherever surface area is more, the boiling point will be more. Right? Great. Now melting point trend I am writing. Careful. This melting point trend, suppose if I take one aryl group, there are two compounds here. One is para position, right? Thus, because it is symmetrical, it will have more boiling point. Next comes your chlorine atom, here one ortho and one para, right? And this will like almost there is one more compound at chlorine one more at meta. So careful students. Due to the symmetry, para will have, or the para isomer fits into the crystal lattice better than ortho and para. That's why para, because of the symmetry. What should you write? Why is the melting point of para more? Because of symmetry. I am just noted, because of symmetry, the para isomer fits into the crystal lattice better than ortho and meta. That's why its melting point is more. Now last but not the least, solubility concept. Solubility, what will happen? The solubility of alkyl groups in water is very, very less. Why? Because of force of attraction between haloalkanes is greater haloalkanes is greater than haloalkanes and water interaction. Understood? Let me write that. Where should I write? I'll write here. Okay? Because the place is less. My handwriting is too big enough. Solubility concept, what should you remember? Careful. The solubility of haloalkanes is less in water, is low in water. Why? because the attraction between haloalkanes and haloalkanes that is very strong. When you see the haloalkanes attraction, see here, haloalkanes and haloalkenes attraction is stronger than haloalkanes and water interaction. Because of this, they are less soluble in nature. Because of the high molecular weight, this interaction, because of the electropositive electronegative atoms, this is stronger. That's why solubility is low. Is it easy? So now boiling point and melting point is one concept. Boiling point and what factors it depends, and solubility and melting point all are covered. Now let us solve one question and see how it goes. Give reasons. Boiling point of alkyl bromide is higher than alkyl chloride. Second, this is a 2 marks question rather. Alkyl halides are better solvents than aryl halides. Explain. I will explain the first one. Boiling point of alkyl bromide is higher than alkyl chloride. Here alkyl is same, bromide and chloride are different. How should you write? Simple answer, write it neatly. First, higher, write in terms of van der Waals forces. Higher magnitude. What does magnitude means? Magnitude means measure. Higher magnitude of van der Waals forces. I told you, right? Because of that van der Waals forces and dipole are more. Use this word, you'll get full marks. Higher magnitude of van der Waals forces in alkyl bromides. That's all. Hence boiling point. Hence boiling point of alkyl bromide is higher than alkyl chloride. That's all. So what will you do? You will take a pencil and you will mark this. You will mark this in the exam. That's all. In alkyl bromide. That's all. You'll get full 1 mark. Next question to answer. Alkyl halides are better solvents than aryl halides. Yes. Why? Right? Only to the point. Alkyl halides are better solvents means I am taking alkyl halides. So for solubility, what is required? Polarity. Alkyl CX is more polar than aryl halides. That's CX is more polar than aryl halides. Okay, right? Just simple. This word you underline. You get this is 1 mark full. This is 1 mark full. So 2 marks answer. Easy. So keywords are very important in board exam. We go for corrections, right? We know what to see. Immediately we give marks. Next question. Let me check whether this is recording or not. I should check, right? Yes, it is recording. So not a problem. Let's proceed. The dipole moment. This is again a 1 mark question, students. The dipole moment of chlorobenzene is lower than cyclohexyl chloride. Why? Oh, nice answer. Very neatly we will answer. Dipole moment. Now basically chlorobenzene and cyclohexyl. Don't write the structures, nothing. First of all, start explaining. They gave you the statement. Start explaining in this term only. First of all, in chlorobenzene, what is present? This is your chlorobenzene. So you start writing like this. Start like this. First of all, in chlorobenzene, what hybridization you are observing? Due to sp2 hybridized carbon atom. So you will concentrate on what is given, you will justify that. sp2 hybridized carbon atom. What is happening here? This sp2 hybridized carbon atom, which is more electronegative, correct na? Which is more electronegative. And because of this, what happens? This tries to drag the electron density and reduces polarity in CCl bond. That's all. So you will not write anything more. Just they say dipole moment of chlorobenzene is lower. Why it is lower? I am explaining. Correct? This is more electronegative, so it reduces the polarity in CCl bond. That's why. Hence, dipole moment is lower in chlorobenzene. So you will finish off the answer. Hence and finish off the answer. Hence chlorobenzene and the dipole moment of chlorobenzene is lower than cyclohexyl chloride. You will simply finish that and complete the answer. So the key words here are sp2 hybridized carbon, More electronegative reduces polarity in CCl bond. That's all. You get full marks in this. This is according to the board key. Easy? Easy. Next question. Arrange the following compounds in the increasing order of their densities. Okay. Densities is what they are asking. So now observe carefully. Density, what is density? Density is equal to mass by volume. Density is equal to mass by volume. It is directly related to mass and indirectly related to or inversely proportional to volume. Okay. So what is this? First of all, benzene, then chlorobenzene. Okay, one is at meta. You have two different halogen atoms. Correct, na? Oh, here you have your molecular weight which is acting. So two halogen atoms means the molecule weight is become more. Correct, na? So subse come. What will be less? Here there are no halogen atoms. So first this one will come. Okay, this is first one. Then second chlorine, there is only one chlorine atom. So second, only one chlorine atom. Molecular weight. Here two chlorine atoms are there. So this is third. Here bromine and chlorine are there. Two different halogen atoms. So fourth. That means the option A is the correct option. Correct, na? So सबसे ज़्यादा is the last one. सबसे कम is the first one. Easy. So just careful. Density and mass. Check directly the relationship. If mass is more, here mass is more, so density is more. Easy. Let us see the next question. The order of decreasing order of boiling point of alkyl halides. So this is in page number 298 of NCERT. Okay, chal. The decreasing order. I have to write the one which is very less boiling point at the end. Okay, careful. So first of all alkyl groups are same, right? In everything, alkyl groups are same. All are same. Okay. So what you should remember? Answer. You will understand. Sorry, I have cough actually. For same alkyl group, if the alkyl groups are same, what will happen to the boiling point? The boiling point depends on what? The boiling point depends on size of halogen atom, size and molecular weight of halogen atom. Now you only tell me among everything which will be highest. Actually Ri is highest, सबसे ज़्यादा. Then this according to this, and then RBr, then bromine, chlorine, iodine, na? Then chlorine, सबसे कम RF, because halogen, this is smaller molecular weight, smaller size atom. This is larger molecular weight. That's why this boiling point will be maximum. Now here, what is the option which is there? C, correct? Now, what is happening here? Size and mass of halogen atom is increasing. So van der Waals forces increase. What concepts did I remember in this? Size increases of which one? Halogen atom. Mass increases halogen atom, and van der Waals forces also are increasing. Van der Waals forces are increasing. So what will happen when size increases, mass increases? That the force of attraction between the halogen as well as alkyl halide increases. Alkyl group increases. So boiling point increases. So this is the concept. This is only for the halogen atom. X atom or halogen atom. Easy. Next question. So which of the following is liquid at the room temperature? Okay, that is what they're asking. Boiling point against is shown here. Okay, so see here. This molecule is given. The boiling point is given here. Molecule is given, boiling point. This one and boiling point. This one is boiling point. So first thing what you should remember is, I will write in the order, one after the other. Then you can understand it carefully in terms of what. Listen. First of all the alkyl groups are same or different? They are different. Okay. Temperatures I didn't understand at all. Simple thing. Among everything, first of all, preset knowledge of everything you should remember is CH3F, CH3Cl and CH3Br. These three compounds I will first explain. They are all gases at room temperature. This you remember, gases at room temperature. This you remember, at room temperature they are gases. Okay. Sorry. Here the weather is very cold. I got cough. CH3I, always it remains liquid. Okay, it remains liquid. Remember this and tell you what it is. Remains liquid at which one? At room temperature. Both at room temperature only. Okay. Now, Why it is remaining at room temperature? Because of high molecular mass. Because of high molecular mass, it is remaining liquid, because van der Waals force of attraction is strong between both of them. Correct na? Right? Because of the high molecular weight, what is increasing? High boiling point also will be there for this. Okay. Now, among all, without seeing this temperature also, you can say na liquid at room temperature is CH3I because of high molecular boiling point, high molecular weight. So how will I justify? CH3I is a liquid at room temperature because of what? Because of high molecular weight. Means it is CH3I higher van der Waals forces. I write here higher van der Waals forces of attraction, van der Waals forces, and hence of attraction, and hence boiling point is high. That's all. Remaining all are gases. Easy? Very easy. Next question. Which of the following are gases at room temperature? Okay. Once again, same thing. As I said, careful. Now, molecules, what are given? This is C4, this is C5, this is C3. So, the following are gases. Simple now, I said, na, whichever are whichever are low molecular weight, they are liquids or gases. Careful. Whichever are low molecular weight means they remain gases because the attraction is less among them, gases at room temperature. So remember this concept. Okay, vice versa. High molecular weight, they'll remain liquids. That is what we discussed here now. See here. That's all. Now low molecular weight, which one will remain gas here? CH3. Cl will remain gas. Remaining all this I, it will become liquid because they are strong enough to hold the molecule. Okay, next option. Which of the following isomer has the highest melting point? This is there in CBSE sample paper 2021-22 and NCERT page 299. Which of the following isomer has the highest melting point? Okay, highest melting point. Okay, as I told you, careful in melting point order, or para first, then ortho and para, then meta last. Correct na? Yes. Now among all these highest melting point which I said as the order, what should you remember now? Careful. Your most important thing is check for the para. Where is para? First 1, 2. This is ortho and para. No, ortho. Yeah, this is ortho and no, basically if I have to take, this is ortho and para. Either ways, ortho and para. 1, 3. This is your meta is there in this. Then 1, 4. Okay. 1 and 4. Next, this is para. All isomers have same melting point. This is wrong. So check here. Careful. Or para isomers, I said na. This is 1. This is 1. Okay. So here, this is your ortho. Para is already there. Ortho and meta. Ortho and para. So here, highest they said na. One second. Here, what? Let me write 1 minute, student. 1 minute. 1, 2, right? This is 1. This is 2. Okay, this is first one. I'll take my eraser. Erase. Okay, let me erase this so that I will write the next one. This is first one, first option. Okay, second option, I will make it easy for you. 1 and 1, 2, 3. Third option, 1 and 4. Correct na? Oh. So according to the order, we said सबसे ज़्यादा para isomers are symmetrical in nature. Correct na? So here in this para isomer concept is they are symmetrical. Okay. Then they fit into crystal lattice. When they fit into the crystal lattice, what will happen? I require a lot of melting point. I require more temperatures to melt it. So for this, it will have high MP. Correct na? So option C is the thing. So para, this will be highest among all. Correct na? So first para will be more, then orthomerism. Option A, para. So option A. So para will be more because of the crystal lattice and symmetrical in nature. then ortho, then meta. Okay, last, this is what we discussed here. See here, see this. I'll go back. I've explained this. See this here. Correct now? Melting point of para is more. Perfect. Let us go back to the question again. Next question. Now we will see the chemical reactions. Careful. The physical properties are over. Till now, what did we do? We did nature of chemical bond, CX bond, nomenclature. We did physical properties. We did preparations. Now we are going to do chemical properties. So basically, your chemical reactions, they show three varieties. Your haloalkanes. I'm taking about haloalkanes. Chemical reactions of haloalkanes. Haloalkanes basically are going to show first type of reaction, nucleophilic substitution reactions. Second type of reactions are elimination reactions. Third type of thing are reaction with metals. Reaction with metals. Is this okay? Yes. Now we will see the first type of reaction, that is nucleophilic substitution reactions. Careful. See this. Nucleophilic is one. Elimination is one. Reaction with metal is one. Woods reaction is one more. That is with the metal. So basically, first with potassium hydroxide, what is a nucleophile here? OH. X. This is going to replace this, and here you get product. This is the conversion of alkyl halide to alcohol. Second, in the presence of water, what is a nucleophile here? See this. I am opening the water molecule. This is OH and this is X. You get again alcohol. Second, in this case, you're breaking the bond in this way. Na plus and OR minus. So, this is your ether. Conversion of alkyl halides to ether. Next, acetone. This is your Finkelstein reaction where you're converting alkyl chlorides to alkyl iodides. Again, this replaces chlorine, this replaces iodine. Then lithium aluminum hydride reducing agent where a reduction happens, where this adds a hydrogen to this. So see here, conversion of alkyl halides to hydrocarbons. Then elimination reactions. Careful. Here elimination reactions is you're trying to replace dehydrohalogenation reactions. You're removing water as well as you remove halogen and you'll get an alkene. So elimination reactions involves the formation of alkenes. I'm going to explain in detail now soon. So careful. Next, reaction with metals. This is nothing but addition reactions where you are trying to use or expand the chain. Okay. So this further, hydrolysis becomes, you do the hydrolysis, you get the alkane, means ethyl bromide to hydrocarbon. Basically, it is not, if I have to tell, not Brigance reagent, but you're trying to expand the expand means simply you are trying to make the conversion of ethyl to into ethane, ethyl to ethane, methyl to methane, propyl to propane, in that way. Next, Woods reaction. This is basically expansion of chain. In Woods reaction, you are trying to add or elongate the chain, where you are increasing the number of carbon atoms. Here, with the sodium metal, you're trying to convert this. Okay, Woods reaction. So gradually we will go now in detail. We will see the reactions. So these are the reactions of chemical reactions basically. Now in detail we are going to study about SN1 reaction and SN2 reaction. Alright, let's start. First of all, we will understand what are nucleophilic substitution reactions. Nucleophilic substitution reactions. Very, very important. Okay. Now, first of all, what happens is nucleophile is there. Okay. This nucleophile, it attacks an halo or alkyl halide which has difference in polarity. Why? X is more electronegative, it drags the electron density, it becomes partially negative. This one becomes partially positive. Correct na? So when this one becomes positive, nucleophile comes and attacks to CH3. So this is your nucleophile. This is your alkyl halide. And you will be getting your nucleophile attacks from backside your CH3. What is this? This is your product formed. Okay. And your X is out. This is called the leaving group. Simple na in nucleophilic substitution reaction. Now, in this nucleophilic substitution reaction, it is initiated by the nucleophile. This is important. That's why it is called, because it is initiated by the nucleophile, it is called nucleophilic substitution reaction. So, nucleus loving species means which forms the product. Okay, means which goes and joins with the positive charge. So, that's why, because it is initiated by the nucleophile, it is called nucleophilic substitution. There are two varieties of NSRs, nucleophilic substitution reactions, are of two types. One is SN2 reaction, one is SN1 reaction. Now let us start the SN2 reaction. Full form is bimolecular nucleophilic substitution reaction. Bimolecular nucleophilic substitution reaction. This one. Okay. So bimolecular, bi means 2. Nucleophilic means N. Substitution means S. SN2. Easy. So how is this reaction? Let us see. Now I am taking one nucleophile. Okay, oxygen has negative charge. I am taking one alkyl halide. So what will happen? This OH goes and attacks this. This bond breaks. Correct na? What will you get? You get OH attached to CH3 plus Cl minus. This is simple. Correct na? Yes. Now in this, two molecules are participating. How is this mechanism in SN2? Careful. The mechanism of SN2 reaction is, first your OH group, whatever is there, goes and attacks this alkyl halide. There are a pair of electrons. This picks up this. It becomes partial negative charge. This becomes partial positive charge. So OH goes and attacks the positive. So what is going to happen? There is formation of a transition state. Means a temporary state which is formed. It temporarily goes and attacks to your carbon atom, and which has 3 hydrogens here like this. Now after this, the Cl bond, whatever is here, that slowly attaches. Correct? Now this is your forward reaction, this is your backward reaction. Careful. What is this stage called? This state is called transition state. What is called? Transition state. Now further, what happens during product formation? The bond breaks here and there is completely changing configuration of your molecule, and your Cl minus is out. First, now careful, observe the kinematics of this. First of all, this reaction follows second order kinetics. How does it follow? It follows second order kinetics. Why second order kinetics? Because the rate of the reaction is dependent upon the rate constant, and two molecules are participating in the particular reaction. See, there's two molecules are participating. Now, rate of the reaction is directly proportional to the nucleophile as well as the substrate. Now, substrate is what? Your alkyl halide. That's why it is called second order kinetics. Is it okay? So, but it is a single step concerted reaction. It happens in single step. This is what is important. This is first point. Second point is, it is single step concerted reaction. It is going to concerted reaction. It happens in single step. RXN means reaction. Now, what is the order of reactivity? Because the stability depends upon the carbocation stability, correct? So, order of reactivity, what should I write? The order of reactivity is primary. 1 degree is more preferred because it is easy for the nucleophile to break the bond, correct na? Then comes your secondary, then comes your tertiary, very much then tertiary. Okay, so for example, primary CH3X is first preferred. Less hindrance. There is very, very less hindrance in this. There is no problem at all. Correct. Then comes your secondary halide, CH3. There are 2 hydrogens attached. Here 1 hydrogen, here 2 hydrogens. Then comes your tertiary. There is only 1 hydrogen and 2 alkyl groups. No, this is methyl, this is primary, this is secondary, and the last is tertiary. Tertiary is there are 3 alkyl groups attached and 1x, CX, 1x. This is S. There are a lot of bulkiness in the tertiary. That's why it will not undergo difficult for it to undergo SN2. Less hindrance means primary is more preferred. This is very important because of the less hindrance, OH nucleophile can go and attack. Correct? Now, if this is okay, methyl group and everything. Suppose halogens are different. Now here what did you take? I took chlorine. Suppose if order of reactivity of halogens are different. Their alkyl reactivity if halogens are different. So halogens are different. What happens here? Because size of the halogen differs, right? So Ri, what will happen? I prefer it more than RBr. I prefer it more than RCl. I prefer it more than RF. Why? Here what is happening? Weak bond. The bond is very, very weak bond strength. When the strength is weak, what will happen? I can easy to break the bond. Then it will go and attack. This is nucleophile, right? It will go and attack the methyl group. Here bond is strong bond. When what will happen? Difficult to break the bond. If it is difficult to break the bond, If it is difficult to break the bond, where will it go and attack the alkyl halide? Correct, na? So that means you should remember one important thing, that both in your SN1 or SN2 reactions, careful is whenever you are trying to take the concept, what should you do? You have to remember the order as 1 degree, greater than 2 degree, greater than 3 degree. Correct, na? This is for which one? This is for the alkyl groups. But when it is for the halogens, Ri more preferred than RBr, more preferred than RCl, more preferred than RF, because of the easy to break the bond. Okay, here in terms of carbocation formation, that is tertiary, primary is less bulky, primary will form a stable carbocation. You see, easy. Now let us see one more thing before I proceed to one more. Okay, so let us see one more thing. The different reactions of what we have using your nucleophile. So first of all, I am going to take one CH3Br. Okay, this is one molecule where I am showing you the different reactions of nucleophiles which you should remember. Okay, first of all, I am taking sodium hydroxide. Now what is a nucleophile here? OH, Na plus and OH minus. So bromine is replaced by OH, so you get methanol. This is one conversion. Okay, let us take one more. I am taking NaOCH3. So here this is the nucleophile, this is the electrophile. So I will be getting ethers. This is the conversion of alkyl halide to ether. Next, I am taking KCl. Now this is positive, this is negative. So what will happen? I will be getting methyl cyanide. This is methyl cyanide. Okay. Suppose if I take AgCN, okay, ambidentate nucleophile. So this is positive, this is negative. Here in this case, you will be getting methyl isocyanide. This is methyl cyanide. This is methyl isocyanide. So what is the difference? I'll show you here. In this case, K positive, C triple bond N, yes, this is negative. Okay, that's why it goes and attacks. In this case, Ag positive and C triple bond N, the lone pair is there on this nitrogen. That's why that goes and attacks the carbon atom. Got it? That is one. Next, KNO2 is 1. Here, what is the product? You will be getting methyl nitrite. This is methyl nitrite, NTRITE. What happens here? Potassium plus and oxygen. The negative charge is on the oxygen atom. So that goes and attacks the carbon atom. Next, same thing. If I take AgNO2, careful. The product which I get is this one, nitroalkane or nitromethane. In this case, what happens? Silver the lone pair of electrons are present on the nitrogen atom. That's why the attack is to the carbon atom. Is it okay? Next important thing, what else do we have? Okay, we have, okay, then after, okay, then we will take lithium iodide. Okay, so lithium, methyl, CH3Li. So here, what is electrophile? This is electrophile. This no, this CH3. This is the nucleophile, and this is the electrophile. Metal atoms, right? So what do you get? It goes and replaces the bromine, and you get an hydrocarbon, and LiBr is one more. Correct. I think this is clear. We'll go to the next page. Next page. Further reactions of CH3Br. Easy. CH3Br, what did we take? Now we will take lithium aluminum hydride reduction. Lithium aluminum hydride, this adds what? This is going to the nucleophile is H minus. So this goes and adds, and you will be getting a methane. So methyl bromide to methane. Okay. Now one more electrophile. One more nucleophile. 3C double bond O, silver acetate. Okay, silver acetate. Silver acetate, what is the this one and this? In silver acetate, careful, the bond, the nucleophile here is CH3, CH2, C double bond O, O minus. This is the nucleophile. So bromine is removed by the AgBr, and you will get CH3, O, CO, O, Ce2, CH2, CH3. Is it okay? Done. Next comes your silver is over. Okay, I'll take methylamine. So methylamine. Now here in methylamine, careful. The hydrogen breaks and it adds to this. See this NH, CH3. Okay. Easy. Then suppose if I take ammonia. Okay. Then again NH goes and HBr is removed, and your NH2. This is the conversion of methyl alkyl bromoalkane or alkyl bromide, methyl bromide to methylamine. Careful. Next, suppose if I have I in the presence of acetone. Here I minus is a nucleophile. I will be getting CH3I, Finkelstein reaction. And you will be getting CH3I and NABR is the byproduct. Is it easy? Easy. These are the different reactions. So practice this and this. It is easy for you. Simple, nothing much. So concept, what you should remember before I go, note it. Take the screenshot or whatever it is. Note it. So careful. Till now we have discussed what we have discussed. In types of reactions, once I'm summarizing, in types of reactions, we have discussed, what is that? Nucleophilic substitution reactions. In that, I discussed SN2 reaction. Then in the different varieties of nucleophilic substitution reactions, I took CH3Br and I've shown you a lot of reactions, almost, 8, I think, let us count once. How many did I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, almost 12 nucleophilic substitution reactions, NSR reactions I have taught. Correct, na? So we need to learn SN1 is there. Let us learn SN1 and again summarize it. So the next variety is SN1 mechanism. Careful, see this. In SN1 mechanism, what is happening? First of all, tertiary, yes, here tertiary alkyl halide step 1 is preferred more. In SN2, less steric hindrance. Here you should remember more stable carbocation. That is, tertiary is more preferred in this case. Tertiary 1 degree is more preferred. Okay, then 2 degree, then 3 degree. 3 degree, 2 degree and 1 degree. Here first of all there is a formation of stable tertiary carbocation. Tertiary carbocation, first thing. After the formation, in step 2, the nucleophile comes and attacks the tertiary carbocation. Then when this happens, there is inversion of configuration. The complete molecule inverts. See this. And finally, what happens? The nucleophile, when it inverts, when the nucleophile attacks from this side, then what will happen? The configuration is retained. That means in SN1, both inversion and retention are happening. Retention are happening in SN1 reaction, both. So here nucleophile attacks from same side as the leaving group. That is very important. Wherever leaving group is there, this is your leaving group. Wherever nucleophile attacks from the same side of the leaving group, when it attacks here, see here, leaving group is here, nucleophile is here, then the configuration is retained. So in SN1 mechanism, careful, it happens step by step. In SN2, it happens in one step. Correct, na? So what is the order of reactivity? Before I go, see, this is one more SN2. I summarized here. I'll show you. What should I remember in SN1 carefully? Here, rate of the reaction directly proportional to alkyl halide. Only alkyl halide. That's only one substrate. Rate constant. It depends on only alkyl halide. That's why it is first order reaction. Only one. Correct. So this happens in two steps. Correct? 2 steps it happens. SN1 mechanism. What is the order here? Tertiary is more preferred because of the formation of the carbocation bromine. Then comes your secondary. Yes, because the bulkier forms a stable carbocation. Then comes your primary CH3, CH2Br. Then finally, it is last preferred is methyl bromide. Okay, so stable carbocation. Most important thing is SN1 speak in terms of carbocation formation. So tertiary carbocation more stable than secondary, then primary, then methyl. Okay, so if the carbocation is stable, yes, then the substrate gives SN1 fast. What is the conclusion of the story? If carbocation is stable, then what will happen? Then substrate gives SN1 reaction. Okay, easy. Remember this. These are the points for SN1. Now SN2, once again summary. This happens, the nucleophile comes and attacks the leaving group. It forms a transition state. Then finally, the leaving group goes off and you get the same configuration. There is no inversion. In SN2, there is no inversion. But in SN1, there is inversion and retention. Is it okay? Easy? Easy. Okay. Now finally, I have given differences between SN1 and SN2. See here. SN1 is preferred by tertiary. SN2 is preferred by methyl and primary. So in SN2, the hindrance should be less. In SN1, the hindrance is more, but stable carbocation. In SN1, nature of nucleophile has no effect. There is no problem. SN1 basically uses weak nucleophiles. Remember this. SN2 requires more reactive nucleophiles. Strong nucleophiles is what it requires. Effect of solvent, these are all required for your MCQs. Remember, in SN1, you require a solvent which is polar protic solvent. In case of SN2, you require polar aprotic. What are polar protic? What is apolar? I'll explain you. Remember this. Let us solve the questions now. Correct. The correct increasing order of rate of the reaction towards nucleophilic substitution reactions. Okay, once let me see whether it is recording or not. Once again, we need to check always. It is recording. Yes, I need to check. Otherwise, waste na. Alright. The correct increasing order for the rate of the reaction towards nucleophilic substitution reactions. Careful. First of all, in nucleophilic substitution reaction, did they say any SN1 or SN2? Nothing they said. Order of nucleophilic substitution. First of all, what is the difference between all? Now see this. What is this group? This is electron releasing group. This one, this one, electron withdrawing groups. Okay. So, chlorine also electron withdrawing. It also tries to drag the electron density, correct? Na? It also drags the electron density towards itself. Correct. Now, what is the concept? what should I remember in my mind is, if electron withdrawing groups are there, if the electron withdrawing groups are more, then reactivity of haloarenes towards NSR is increasing. Okay, NSR increase. Why? Because they are pulling it. When they pull, there are two different charges which are created. Then automatically what will happen? The electrophilicity, this will pull the electron density, and the electrophilicity of the carbon, what is there? Yes, it starts, means this is pulling, this will get the charge, negative charge, this will get the positive charge. So what will happen? Nucleophile will come and easily attack it. Easy, once again. Electron withdrawing group increases, nucleophilic substitution increases of which one? Of the particular molecule. Electrophilicity means the concept of electrophile, electrophilicity of aromatic carbon. Aromatic carbon means the carbon atom which is there here, the carbon atom which is there here, and here. What will happen? It will increase. Aromatic electrophilicity. Electrophile is waiting for the nucleophile to come and attack. Then what will happen? The nucleophile will come and attack it. When electrophilicity increases, the nucleophile attack increases. Easy? Attack increases. Correct. It says I want nucleophile, I want electrons, these, because this has pulled, this has pulled, this has pulled. I want electrons is what it says. So automatically when electron withdrawing groups are increasing, electrophilicity increases. Easy? Now other way around, if electron releasing groups are there, it goes on releasing electrons. Then where is a requirement? There is no poverty which is created. Correct na? So more the electron withdrawing group, more the NSR. Careful. Once again, more electron withdrawing group, more nucleophilic substitution reactions will happen. Directly related. Now you tell me, increasing order of the rate of the reaction, which will have more? Yes, this will have less because electron releasing. Then B. Then so सबसे ज़्यादा will have, or this will have maximum compared to this because of more electron withdrawing. Easy? Remember this. So the one which is highest is the last one because of EWG groups. Easy? Easy. Careful. Next question. There is no, okay. And one more thing I have to tell you. I forgot to tell you. In, suppose if they're asking you this question, in SN1 reaction, one just out of the box question. In SN1, find the order of reactivity for SN1 reaction is what they're asking. SN1 reaction. Okay. What do they ask? They've given you a question like option A, there is one molecule like this. There is one molecule like this. Okay. There's one molecule given. Then there is one more molecule which is given like this. Okay. There is one more molecule where they have given this. Now, first of all, how should I arrange the order? Find the order. Now tell me, for SN1 I require bulky groups or less bulky groups? No. In SN1 I have to remember stability of carbocation is important. Stability of carbocation. Repeat along with me. Stability of carbocation is important. So सबसे ज़्यादा carbocation which is stable, this one. Correct na? This is resonance stabilized. This is stability of the carbocation. सबसे ज़्यादा this will prefer. सबसे कम वाला this, because this is less bulky. Correct? So primary carbocation less preferred, then this carbocation, then this one, this carbocation. Correct na? So stability of carbocation is more preferred in this case. So whenever SN1 is asked, talk in terms of stability. Whichever is resonance stabilized, that will prefer more SN1. That's all. Easy? Easy peasy. Next question. Any other question? Okay. So stereochemistry. Now we are going to study about chirality of the molecule. Careful. Whenever we are going to the chirality concept, little concept, I will explain stereochemistry, then we will go to chirality. Now SN1 and SN2 is over. Now we will talk about stereochemistry of SN1 and SN2. Stereochemistry of SN1 versus SN2. Careful. Yes. In SN1, inverted product is formed or SN2? Correct. SN2 reaction gives inverted product. Okay. SN2 reaction gives inverted product. Okay. But SN1 reaction gives racemic mixture. Racemic mixture. What is this? It goes through a process called racemization. Racemization. I'll tell you what it is. Understand this. In SN2 reaction, let us take an example. I'm taking on SN2. Okay. OH is here. It's going. I'm taking a molecule SN2. Let's see. SN2, what do I require? I require attack of the molecule. Correct? It goes. Whether it is taking bulky or not, let us see how it goes. CH3, there is one H. Here what happens? Here the hydrogen atom is smaller. So I can go with this hydrogen atom smaller molecule and I am having bromine on this side. OH comes and attacks this because bromine tries to drag the electron density towards it. So what do I get? I get an OH which is attached. One CH3 is here. One your group C6H13 is here. And your hydrogen atom is here on the rear end. And the bromine atom is outer. So when OH is attacking on the opposite side, carbon-bromine bond is formed. So inversion of configuration. Correct. When it is attacking from the opposite side, here the bond is formed and completely from here the groups have shifted to the other side. So CBr, so the inversion of configuration happens here. Correct. Now, so let us take one SN1 now and see SN1. I am taking the same molecule, a little bit I'll change the groups Br. And you have your hydrogen atom here. Now I am forming a carbocation first in SN1. Okay, so now CH3 and I am forming a carbocation C2H5. I am breaking the bond and forming a carbocation. So now OH is attacking here. It's coming from this direction. So what will happen? It will give me two varieties of compounds. Two varieties. It is attacking now. It gives me two varieties of compounds. What are they? I'll write it in the next page. It is forming two varieties of compounds. On the attack, I will take the same molecule again for your reference. This is your hydrogen. This is your C2H5. And your OH minus is attacking this variety. Variety number 1 is you get a molecule which looks like this with this configuration. Second is you get a molecule. Now this is C2H5. This is CH3. Okay. So OH is here. Now see this OH, where am I shifting? I am shifting OH down, C2H5 here and CH3 here. So what happened to the configuration now? There are two compounds A and B. So both are same. It is butane to all. But here the direction of the atoms are different. Direction of atoms are different. So what am I doing? I am rotating the molecule. I am holding it and rotating the molecule. From here, I rotated the molecule in this direction. So H has gone above, OH has come here. So what is this compound called? This is called plus or minus. Put it in the closed brackets. This is called butane to all. Butane to all. This is called, these two are called racemic mixtures. What are they called? They are called racemic mixtures. Racemic mixtures. Yes, simple, na? Simple stereochemistry. There is nothing big. So now what is the order of reactivity for SN1? Order of reactivity for SN1. Reactivity of SN1. Careful. First of all, in SN1, tertiary halide, more preferred than secondary halide, more preferred than primary halide, more preferred than CH3X. For SN2, CH3X first preferred, then primary 1 degree halide, then 2 degree halide, then 3 degree halide. Easy? Very easy. Okay, so nothing to get confused. Easy, very easy reactions. Careful. So next comes here elimination reactions. SN1 is over, SN2 is over. Now I have to concentrate on elimination reactions, then solve one more question. Okay, so let us go. What actually is elimination reaction? Elimination reaction. Okay. He said na, elimination reaction, SN1, SN2 reaction, reaction with metals. Now elimination I'm explaining, see here. What is elimination reaction? This is also called as dehydrohalogenation reactions. Sorry. Okay, what happened? Okay, these are also called dehydrohalogenation reactions. Dehydrohalogen. Shall I check whether it is recording? Because suddenly a window popped in. It's okay. Dehydrohalogenation reaction. Okay. Now, what is this? Basically, for dehydrohalogenation reaction, what do I require? I require a haloalkane with beta hydrogen atom. This is my requirement. A haloalkane with beta hydrogen atom. When you introduce alcoholic KOH, then it will become alkene. That's all. This is elimination. What a big deal. Nothing is there in this. I'll take you an example and see. Now, what is beta hydrogen atom? Let us see. There is one carbon chain like this. Okay. Now, bromine is present here. And here hydrogen atom is present here. Okay. Now, this is alpha hydrogen. This is beta hydrogen. The one which is adjacent to the substituent where is present. Now I am introducing an alcoholic KOH. The nucleophile is OH. So first of all, the electron density, this bond shifts here. When this bond shifts here, H goes and attacks the hydrogen, and there is a formation of a double bond, that is CH3CH double bond CH2 plus water molecule, and your bromine is out. That's all is dehydrohalogenation. Easy, na? I'll take one more example, a bigger one. This is A and this is B. Suppose I take CH3, this is CH2, this is CH, this is your CH, this is CH2. Okay, now this is your bromine is here. Now this is alpha hydrogen, this is your beta hydrogen, this is your beta hydrogen, this one. Okay, this is your H1, this is H2, this is H1 hydrogen 1, this is hydrogen 2. On either sides are beta. Correct, na? Now, when you have such confusion, here directly I took and I eliminated. When you have OH minus, it's going to form two different products. First, you have to dehydrohalogen, means you will remove HBr. Hydrogen also you should remove, and Br2 also you should remove. I should remove hydrogen, I should remove dehydrohalogenation. Na? Both I have to remove. So first thing, when it takes, the first thing, double bond forms here or double bond forms here. Both the sides I can take out hydrogen. So first concept, CH3, CH2, CH, double bond, CH, CH3. Here, this is the major product. Stable alkene. Next one, CH3, CH2, CH2, CH, double bond, CH2. This is the minor product, less stable. This is more stable, this is less stable. Now what is this? This is called, careful. Okay, will you tell me in the comment section what this thing is called? Something with S? Okay, tell me. The highly substituted alkene means the alkene which is having more number of hydrogen atoms. Highly substituted means it has more. Okay, I will not tell this. You will tell me in the comment section what is this rule called. So the one which is having the highly, so on either side see here symmetrical, the highly substituted product, it's the major alkene. Tell me in the comment section what is this rule called. So this is the elimination reaction. Easy. Before we go to the question, let us write reaction with metals, the last one of the reactions, reaction with metals. Careful. Reaction with metals is nothing. You are taking RBr. Then what you are introducing? You are introducing magnesium in dry ether. When you are using magnesium in dry ether, you get RMgX. This is, sorry. RMgX. This is called Grignard's reagent. Grignard's reagent. So this RMgX, what will you do? If you take this RMgX and if you try to hydrolyze it, you're adding water, H plus and OH minus. So what will happen? It's going to convert into RH, hydrocarbon, plus MgOHX. That's all. So it's a conversion of your Grignard's reagent or the alkyl halide using Grignard's reagent into hydrocarbons. Same thing like, Woods reaction also. Same thing na. In Woods reaction, what will happen? I will add here. Woods reaction, you are taking alkyl halide, you are adding metal, one more alkyl halide. Woods reaction, you will get here RR plus NX. RR plus NX. This is one more reaction. Easy. So these are SN1, that is SN2, this is elimination, this is reaction with metals. Now let's start with the concept. Let us start this question. Reaction of C6H5CH2Br with aqueous sodium hydroxide follows. Okay, so this is an aryl halide with aqueous sodium hydroxide. We did na? Aqueous sodium hydroxide means what? This is the nucleophilic OH minus. Now they are for saying follows which one. So this is an aryl ring. So what should you remember? Resonance stabilized. If it is resonance stabilized means what should you remember? I have to go with SN1. Whether it is I have to go with SN2. Careful. Bulkier groups are not preferred in what? SN2 or SN1? Tell me in the comment section. Bulkier groups are present in SN1 or SN2. Immediately type. You are listening to the video. Immediately type. Careful. Here in this case, your open the chain, CH2, this is Br. This is a smaller group. There is no bulkiness or nothing. Don't worry about this. It has two hydrogen atoms. Correct na? So what will it prefer? It will go and prefer with NaOH. It will prefer which reaction? SN2 mechanism. SN2, because look at this group. So in SN2, the option first is order is always methyl greater than primary, greater than secondary, greater than tertiary. You see, very easy. Very easy. Chalo. Next question. Which of the following is most reactive towards SN1 reaction? Okay, which is the most reactive towards SN1? There are different examples. SN1, what concept should I remember? SN1 always depends upon tertiary carbocation stability. Carbocation stability, correct na? Stability. This is what it depends on. Now, among all compounds, which is more stable? See this. Okay, one aryl ring, two aryl rings are there. You see where your bromine is attached. In this case, bromine attached. In this case, bromine attached. In this case, bromine is attached to water. So in SN1, I want tertiary carbocation or resonance stabilized. So I should remember higher stability of carbocations, more reactivity. Correct na? more SN1 reaction. It happens more SN1 reaction. So tertiary is more stabilized. So which one is tertiary here in this case? Because here it has two phenyl groups. See this. There are two phenyl groups. Here only one. Here also two are there. Here one. Here one. Compared to this, here you have one more alkyl group. Means it is more bulky. So two phenyl groups and one methyl group in this case. That's why this will be more stability for more stable carbocation. That's why I'm marking this. Correct? So more of the resonance stabilization or more of stability, more will be the SN1 group. So look for bulky ones and immediately mark it. You see? Next question. A Grignard reagent may be made by reacting magnesium with Grignard reagent. How are you preparing? Easy. I am going to take methylamine, diethyl ether, ethyl iodide, ethyl alcohol, ethyl iodide. Because I am going to take ethyl iodide, I am going to add magnesium. I am going to take dry ether and add the CH3, CH2, Mg. So ethyl magnesium iodide. Simple. So let us take a small break and then again do the video. Alright, now let's go with the next question. In the earlier question we have done how to prepare your Grignard's reagent, right? Made by reacting magnesium. Alright, now let's go to the next question. Question says, in SN1 reaction, the racemization takes place. It is due to what? So in SN1 we very well have studied racemization takes place because of what factors? First, it undergoes in SN1. It undergoes basically step by step, correct? Na? It undergoes in two steps. So in this SN1, basically it involves carbocation, correct? Which are most important, they are planar, correct? So that planar structure can attack from both the sides, isn't it? That is what we have seen in the SN1 reaction. So what clue you should remember is, this in SN1 reaction, first of all, it undergoes or it involves, what does it involve? It involves carbocation. Which carbocation it involves? It's going to involve, other than the SN2, it involves tertiary carbocation, correct? Now in this tertiary carbocation, when it is involving, and that too, which has planar, that's very important. This carbocation, whatever you are taking, this carbocation, the main characteristic is it is a planar structure, planar. And when it is planar, it has sp2 hybridized carbon atom. Alright, now what is the speciality of this sp2 hybridized carbon atom? Because the structure is planar, the OH minus can attack from this direction, the OH minus can attack from this direction as well, both the sides. So because of this, what are you getting? You're getting a mixture of both. One is the plus as well as minus, correct? No? So SN1 is involving racemization due to what? Inversion of configuration, correct? Retention of configuration because of what? Planar sp2 carbon. So you remember, students, earlier I already said, if I have to say one, let us go back and show you. See here in SN2 SN1 tertiary, both the things we are taking, because the structure of this carbocation is in one plane. That's why I can attack from this direction and this direction. That is what we said. Because of this characteristic, we are going to have both inversion and retention. That's why A and B both are correct. Next question. The order of reactivities of the following alkyl halides for an SN2 reaction. Okay, SN2 is easy. SN2 basically it depends upon what? It only depends upon less steric hindrance compound. This is what is the key factor for this, less steric hindrance. Now what did they give me? They gave me alkyl halides. So if I have to do this, less steric hindrance alkyl halide. Now what about your halogen? I want a weaker CX bond, correct? Na? Weaker CX bond. CX bond means the halogen, the bond should be so large that it easily breaks. Weaker CX bond. If bond is weaker, reactivity is more reactivity, correct? Na? So you only tell me among all this, which one is weaker among all? Yes, Ra is weaker because the bond The halogen atom is bigger and the size of the bond is also larger. So Ri, Rbr, Rcl and Rf. D option is correct. Correct na? In case of Rf, the electronegativity is more and the bond is closer. So no. Next question. Which among MEX, RCH2X, RCH2, okay, R3, they have given primary, secondary, methyl halide, primary, secondary, tertiary, which is more reactive to SN2. Easy. SN2 always prefers first primary, correct na? It always prefers primary. But here they have given methyl halide also most reactive towards this. So it always depends. The order is CH3X greater than 1 degree, greater than 2 degree, greater than 3 degree, correct na? So here what is that? MEX, that is option A is right. Easy question. Next one. Isopropyl chloride undergoes hydrolysis. So when isopropyl chloride it undergoes hydrolysis, with what undergoes, SN1 or SN2 or both? So they're asking. So isopropyl chloride, if I have to write that careful. So iso, okay, propyl, okay, chloride, okay. So CH3 and this is CH. This is isopropyl chloride. So first of all, this is primary or secondary? You tell me. Halogen, this is attached to secondary carbon or primary carbon? Here there is only one hydrogen. So this is a secondary alkyl halide. Correct na? This is secondary alkyl halide. So secondary alkyl halide means it can undergo SN1, it can undergo SN2 also. Correct na? According to the order of preference is different. Here they are asking whether it undergoes. Yes, because being a secondary halide, it can undergo secondary or yes, it can just undergo SN1 as well as SN2 mechanisms. Both it can undergo. They didn't ask order of preference. They just does it undergo or not. It can undergo because in either sides the structure looks like this. Here you have 3 hydrogens. Here you have 3 hydrogens. So the attack SN1 and SN2 both are possible in isopropyl chloride. Careful. Next question. Tertiary alkyl halides are practically inert to substitution by SN2 mechanism. Why? Tertiary alkyl halide SN2, it is not preferred. This is what they are asking. First of all, whenever somebody talks about SN2, yes, remember SN2 steric hindrance. Yes, steric hindrance, tertiary alkyl halide do not undergo SN2. Careful. The reason here is only it prefers simple less steric hindrance so that the nucleophile goes and attacks. So what reason you will write? You will write like this: due to steric hindrance, tertiary alkyl halides do not react by SN2, but they react by SN1. Okay, SN1 mechanism. Correct na? So SN2 always prefers first methyl, less steric hindrance, then primary by just 2 hydrogens, then secondary which has 2 alkyl groups and 1 hydrogen. Last is your tertiary, which has more steric hindrance, which will not prefer at all. So according to this, what reason? Tertiary alkyl halides are practically inert to substitution by SN2 mechanism. Due to which reason? Due to steric hindrance. This is the concept. Okay. Next question. Alright. The mechanism of SN1 reaction is given by this. Okay. So they are asking, they is given this, the lone pair, then broken solvent separated ion, then leaving group, and this is the leaving group and this is the product. Now the student writes general characteristics based on the given mechanism as, after seeing this reaction, okay, the student has written the general characteristics like this exams. The reaction is favored by weak nucleophiles, okay. R plus would be easily formed if the substituents are bulky, okay. The reaction is accompanied by racemization, okay. The reaction is favored by non-polar solvents. So here they have given SN1. So they are asking to rule out. You know the characteristics, isn't it? One after the other, you know. First of all, the reaction is favored by weak nucleophile. Okay, is that correct? or wrong? Is that correct or wrong? Let us see. So first of all, do I have place? Yes. First of all, for SN1 reaction, careful, okay, for SN1 reaction, the reaction is favored by weak nucleophile. That is 100% correct. What happens if we have strong nucleophiles? Weak nucleophiles are required. But if strong nucleophiles are there in the reaction, strong nucleophiles will favor, instead of substitution reaction, they will favor elimination reactions. Elimination reaction. So that's why I will not prefer strong nucleophiles for SN1. Next thing. If here they said the R plus would be easily formed if the substituents are bulky. Yes, the substituents are bulky. Yes, that is also right, because if substituents are bulky, what will happen? If substituents are bulky, it will form stable, it will form stable or intermediate carbocation, correct na? It forms intermediate R plus cation. So this option also is correct, this also is correct. Third, what did they give me? The nucleophile can, the reaction is accompanied by racemization, they said. Okay, so we know the whatever nucleophile is there, the nucleophile Y minus, it can attack, because here it is the structure, or it can attack the planar, the carbocation is planar, correct na? So it can attack here in this direction, it can attack here in this direction. Why? Because whatever carbocation is there, this is planar in nature, in planar. So because of this planar nature, what is happening? I get a compound which is a racemic mixture, that is racemization, correct na? So third also is correct. Now they said the reaction is favored by non-polar solvents. So this is wrong, isn't it? Because for SN1, as we have studied the characteristics, polar solvents are required. They said non-polar, polar solvents are required. Why polar solvents are required? Because polar solvents help in separation of ion pair, separation of ion pair. This is important. That's why in your SN1 case, we require polar solvents, not apolar solvents or non-polar solvents. So what are all correct? 1 is correct, A is correct, B is correct, 1, 2, 3 are correct. So the option C is the correct answer. Okay, easy, very easy. Now next question, reactions of haloarenes. Okay, so reactions of haloarene, we are almost coming to the end of the chapter. Not a problem, we'll understand. Basically, reactions of haloarenes, first thing, the haloarenes are going to show nucleophilic substitution reactions, NSR, nucleophilic substitution reactions. Why they are showing? Okay, are they showing or not? We have to justify. NSR we wrote, is it correct? Now, careful. First of all, aryl halides are just your alkyl halides will show a lot of nucleophilic substitution reactions, because the bond, we can break the bond and easily replace it. Aryl halides are extremely less reactive. They do not, means I have to provide such reaction conditions to break, because it is resonance stabilized. So aryl halides are extremely less reactive towards NSR. Okay, why towards NSR? Okay, first of all, what factors are there? First thing, concept is they are less reactive. Why? They ask you why. So resonance effect is first thing. Because of this, it does not react with this. It does not show much of your NSRs. What happens here? Suppose if I take one chlorine atom, okay, right? So here alternate pi bonds are there. One chlorine atom is here. 1, 2, 3, 4, 5, 6, 7, 8. So what happens? Because of the resonance, this bond shifts here, and both double bonds can't be here. So this bond shifts here. So what will happen? You will be getting a partial double bond character on chlorine atom. And this becomes minus. So this keeps shifting. This shifts here, this shifts here, this shifts here. So what happens? Carbon chlorine acquires a partial double bond. Now because of this resonance, it's very difficult for me to break this bond. Correct na? So that's why haloarenes do not show, or they are less reactive towards NSR. So like that, I'm just repeating. Note it in your book. carbon chlorine bond acquires a partial double bond character. Okay, and because of what? Because of resonance. And because of this resonance, this becomes difficult for us to break the bond. It becomes difficult for breaking the haloarene bond. Means carbon and halogen. That's why haloarenes are less reactive towards NSR. Is it okay? Next, second point is instability of phenyl carbocation. Instability of phenyl cation. This is the second point why they are not showing, why they are not reactive towards your NSR. Now what is this? Haloarenes cannot follow SN1 path, correct na? Because first thing what happens is, during the first step what happens? Chlorine is here. When you break this, it forms this becomes positive and this becomes negative. Now you tell me here, this is phenyl cation, correct na? So haloarenes don't for SN1 because we get phenyl first step only. In SN1 we have to form a cation, but here what is happening? It forms phenyl cation, correct? This phenyl cation, what happens? This is not stable. Phenyl cation in step 1 when we break, phenyl cation is not stable. It is not stable. So when it is not stable, what will happen? Can it form? So first of all, in SN1 I require, as I told you, SN1 requires a stable carbocation. Here first step only, phenyl cation is not stable. That's why it will not prefer substitution nucleophilic reactions. Correct now? Normally this requires a stable tertiary carbocation, stable 3 degree carbocation. But in this case, phenyl carbocation is not stable. It has so many electrons, but still it is showing positive charge. That is ruled out. Yes. Third reason. Let us go to the next reason. Third reason why haloarenes are not showing NSR is because of repulsions, possible repulsions. That means, okay, let us write, they do not show NSR because of possible repulsions. What is this? Suppose if I take this chlorine atom, okay, now this is your Cl. So what happens now? Nucleophile comes and attacks this. So what happens? This is nucleophile, this also are electrons here. These are all pi electrons, na? Pi electrons. When this comes here, this electron and this electron, they will become repulsions. It will cause repulsions. That's why electron rich nucleophile means here what is happening? There is a fight between electron rich nucleophile and there is a fight between electron rich arenes. That's why when both are fighting, the reactions are not stable enough. That's why your haloarenes will not participate or will not undergo, or rather they do not prefer NSR. So that's why I'm writing hence haloarenes do not prefer undergoing nucleophilic substitution reactions. So let us summarize once again. First, due to resonance. Second, what is the second thing? Because resonance stabilize. Next, due to here unstable phenyl carbocation, correct na? Or due to instability of phenyl cation. Okay. Third one is due to possible repulsions. Due to possible repulsion. Correct na? Yes, this is the thing. That's all. Easy, very easy. Now let us see one more question. Same thing. Haloarenes are less reactive towards nucleophilic substitution. Just now I said na, whatever I have written here, yes, in this page, same thing. Please write point number, same question, same answer. Whatever is mentioned, point number 1, point number 2 and point number 3 noted. Exactly the same way you are going to show everything, and only difference you should do is careful when you are explaining about resonance concept, show the resonating structure. Resonance concept, if I am talking, show the resonating structure of chlorine. As I have shown you, just shift of pi bond. first thing your chlorine is here, 1 2 3 4 5 6, then here, right? Then this bond shifts here, this bond shifts here. So your chlorine atom attains a double bond in this position, and plus, and how many electrons are there? 2 have gone, only 2 are left. So this pi bond shifts here, I get minus, this is bond, this is bond. Now this drops here, this drops here. What will happen further? I'm going to get a, careful, this bond double, here the bond drops, here the bond drops, this gets a negative charge, and remaining all is same. 1 2 3 4 5 6. Next further, this bond drops here and this shifts here. What do I get? Try to show the resonance, because you will get complete marks in that. Okay, the bond further, this bond drops here. Now this, but this, okay, this bond drops here means I should write, I should not write here, I should write minus here, and because this bond shifts here means here I need to write this part, and double bond is here, chlorine 1 2 3 4 plus, like that. Further you are shifting this bond here, and this bond shift goes here, correct na? So you are going to explain in these terms and tell that in haloarenes the electron pairs are distributed, whatever electron pairs are there are distributed, like, you know, they are in conjugation with the, means the electron pairs on the halogen atom are in conjugation with the pi electrons of the ring, and they follow the resonating structures. That's why they are less reactive, correct na? In the second case, when you are showing, you know, in hybridization also, try to show what happens in the concept of this second answer which we have explained, instability of phenyl carbocation, correct na? Draw the phenyl cation and show that why it is unstable. Phenyl carbocation is unstable because of the positive charge, instability, explain that instability. And the last part, what you can also show the comparison between, you know, you have your bond, right? Here in this case you have X, and this is sp2 hybridized, and in this case when you take your normal haloalkane, this is sp3 hybridized, correct na? Right? So you can explain that. So instability of carbocation also you can explain, this concept also you can explain, how you can explain this. So you can say difference in hybridization, both are there. That's why the sp2 hybridized has more s character, and can hold the electron pair, okay, tightly. But in this case it is less s character, so it's difficult to break a shorter bond, correct na? So you can say here s character is more, bond is short. That's why it is difficult for me to break the bond and substitute the nucleophile. Here s character is more, so bond is long, so I can easily break and follow that. That's why this is more prone to substitution reactions. Last but not the least, you can also talk about the fourth point. You can also talk about possible repulsions, correct? Possible repulsions are there between the nucleophilic, the electron rich nucleophile and electron rich haloarene, okay, like that. Okay, easy. So to include all the 4 points to understand why haloarenes will not undergo NSR reactions. Okay, all the 4 points, please remember this. Right, next question, let us see. Okay, see the question. Which compound in each of the following pairs will react faster in SN2 reaction? Okay, SN2 reaction, remember, careful, less bulky group, less steric hindrance, First thing is you should remember less steric hindrance. Now among both of them, first of all, CH3Br and CH3I. Okay, so basically which pairs will undergo faster? Let us see. Here CH3I will react faster than CH3Br because this is better leaving group, correct? Better leaving group, because the bond length is longer, it's easy for me to break. Okay, so this will react. Now in CH3Cl and this tertiary compound, which one is this? This is 3 degree, this is 1 degree, okay, methyl rather, it's primary. So which one steric hindrance will prefer? This one it will prefer. So among both of them, which of the following pairs will react faster with OH? Now if I have to say CH3I in this case, CH3Cl in this case, so compared to this two, this is better, but if I have to compare this and this, these two are better. Is it okay? Yes, you'll write both. Okay, next thing you'll write here, You write first one, in this case second point, in this case. So 1 degree is preferred, this is preferred. Okay, next question. Write structural product of the following write structure of the product formed when the following undergoes SN2 reaction. Okay, SN2 reaction, this has to undergo itself. So SN2 reaction means what is observed? SN2 with OH as a nucleophile. I know this undergoes inversion. Yeah, it undergoes inversion. Alright. So same product, OH minus is attacking. So X is the leaving group. So invert completely. Yes. So write the C2H5 up. Okay. Exactly. Take that hydrogen here. Make that, or if you are shifting, like exactly the same thing you because it is a free hand, my diagram is bad. CH2. Okay. CH2 is given, CH3 rather. CH3. Okay. CH3 is not. Then what will happen here? OH. That's all. Easy. Same compound, they ask you, this is a 1 mark question. Okay, 1 mark question. That's why just you copy the same thing, structure, instead of X, this is a leaving group, and you are writing H. That's all. Then arrange the following in the order of their increasing reactivity nucleophilic substitution reactions. Okay, so nucleophilic substitution, increasing reactivity. As I said, for did they mention any SN1, SN2? No, we already have all primary only. They are talking about methyl alkyl halides. So increasing order, they have to give it increasing. I have to write. So subsec come wala CH3F, then comes your CH3Cl, then comes your CH3Br, then comes your CH3I. Correct, no? That's all. Simple as that. This is easy to undergo because bond length is larger and I can easily break the halogen and replace, right, with a nucleophile. Next question, concept of chirality. Okay, maximum students get confused here. It is easy actually. I'll explain it in detail. So first of all, chirality or concept of chirality, let us go step by step. First of all, what actually is optically active compound? I need to understand what is optically active compound. Okay, optically active compound means what? Now, simple. I have light. Okay, mixture of all light. I am taking one prism. When this light falls on this prism, it will convert all the light in all the directions into one plane. This is called PPL. What is this called? This is called plane polarized light. PPL means plane polarized light. Now, what will you do? You are going to take one solution. In this, there is an optically active compound. There is an optically active compound. So what will happen here in optical active compound? All are in this direction. When you send this plane polarized light, it will have basically means a rotation. It will rotate this plane polarized light in different directions. First direction is it will rotate the plane polarized light like towards this. It will rotate the plane polarized light towards this. In some, it will not rotate, no rotation. Suppose whichever thing happens, if it rotates towards this direction, this is a right direction, this is left direction, this is no rotation or no rotation, then if it rotates to the right, it is called dextro-rotatory. If it rotates towards the left, it is called levo-rotatory. If it doesn't rotate, it is called optically inactive. Is it okay? Yes. Done. So here, what is happening? Dextro and levo-rotatory, these two are called optical isomers. What are they called? Dextro-rotatory, which rotates the light towards the right, and levo-rotatory, these two are called optical isomers. Optical because they rotated the plane polarized light PPL into right direction and left direction. And this phenomenon, whatever they are showing, this phenomenon of rotating the into right and left is called optical isomerism. Optical isomerism. Till here is it clear? Clear. Now I have to understand, after this plane polarized light and everything, I will draw one line, don't mind, vague line. Anyways, concept is important. What we are going to study is a concept called asymmetric carbon. Asymmetric carbon. Careful to understand. What is asymmetric carbon? This, the other name given to this is chiral carbon. Chiral, some say chiral. So chiral carbon. Okay. So what is chiral carbon? A carbon which has all four substituents different. Okay. All four substituents different, and they are sp3 hybridized. 2 points are there for chiral. One is, or they are sp3 hybridized, all single bonds attached, and all the four different substituents, all will be different. For example, on A single bond, B single bond, C single bond, D single bond, all four groups are different. For example, carbon, CH3 group, your hydrogen group, your C2H5 group, your 6C3 group, like that. You have different groups, different atoms, then it is called chiral carbon. How do we represent this chiral carbon? Chiral means they are represented by an asterisk. They are going to represent this by an asterisk. Now I'll show you what it is. Now this chiral carbon, same compound, I'll go to the next page. Suppose this chiral carbon, suppose I take one molecule, okay, so I'll take one molecule, CH3, okay, one C2H5, oh, okay, I will just draw it here, one second. One C2H5, okay, one OH group is here, okay. Now if it forms a mirror image, okay, once again, a chiral carbon atom, if it forms a mirror image, okay, C2H5 and this is CH3, okay. Now what are these? These are, both are mirror images, but when we send this molecule below this, what will happen? Are they superimposing? No, na? OH comes below C2H5, C2H5 comes below OH. So what are these? These are non-superimposable mirror images. What are these called? Non-superimposable mirror images. And so both are there. Non-superimposable is there, and also mirror images are there. I should not put this. Non-superimposable mirror images. So such non-superimposable mirror images are called chiral molecules. Chiral molecules. And these are optically active compounds. These are optically active compounds. Okay, these are optically active compounds. Now, what is the definition of chiral? The objects which are non-superimposable on their mirror images are said to be chiral. Correct, na? What are they called? The objects which are non-superimposable on their mirror images are called chiral molecules. So always write the definition once again. Note it. The chiral molecules are non-superimposable on their mirror images, are said to be chiral or chiral. Easy. Now after this you have to learn a concept of enantiomers. So you understood, I believe, chiral. Enantiomers means what? Okay, same thing. They are non-superimposable mirror images are enantiomers. Stereoisomers, so which rotate the plane polarized, right? Stereo, R-E-O, Stereo. Stereoisomers which are, okay, with non-superimposable mirror images. Non-superimposable mirror images are called enantiomers. Now diastereomers means what? Diastereomers means these are also stereoisomers only, which are, now these are mirror images, non-superimposable mirror images, diastereomers which are not mirror images. Here these are mirror images. These are not mirror images. Both. Careful. Yes. Now here molecule 1 and 2 in this case, whatever is there, no, this molecule and this molecule are enantiomers, and there are non-superimpose. These two are enantiomers. So in the earlier case, enantiomers. So the mixture of these two, both enantiomer, the mixture, and that too diastereomers, ma'am. How to see the diastereomers? I'll show you a molecule, then you will understand that. Okay. Then there's one more concept called racemic mixture. I remember racemic mixture containing a mixture containing two enantiomers, in equal proportions. Two enantiomers in equal proportions are called racemic mixtures. Equal proportion is called racemic mixture. Is it okay? So when I have equal ratios of enantiomers, then it is called racemic mixture. So how is this racemic mixture? It is represented by D and L, or you also have plus, minus, and this. This is also called racemic mixture. So when you mix equal ratios. So if they ask you, like, a small question rather, I'll tell you how to identify. They will ask you identify chiral as well as chiral and achiral molecule in this compound. Okay, in this I'm writing, I identify this. What is chiral means? Chiral should have all 4 atoms different. Okay. Now tell me which is chiral, which is achiral. All 4 are different, so this is chiral. Or 2 are same means this is achiral. So you understood, I believe. Easy. Easy. Yes, very easy. So next, one more question. Same thing, but in a different way if they ask you. What is that? This molecule is here. Okay, there is one molecule here. I'm sorry, I'm coughing. There is one molecule here. Okay, this molecule, right? Then there is one more molecule. Now you tell me which is achiral and which is chiral. On this case, this is your carbon atom where the halogen is attached. Now see here, on one side CH3, on one side Br, on one side H, one side CH2. So this is a chiral molecule, and this one, here 2 hydrogens are there. That's why this is a chiral molecule. Easy, very easy, very easy. Got it? Alright, easy question. So same thing. I have to study in terms of chirality. Chirality means optically active compound which is non-superimposable on the mirror image, is what we said. Now there is one more concept called, suppose this is there in your NCERT. There is one molecule. This is one C2H5. There is carbon. There is one X. There is one C2H5, and there is one more group. Correct, na? So now this is your chiral molecule. Now chiral molecule, careful, here it can form, like if I have to write, because the rotation wise it can form 2 different compounds, na? So say dextrorotatory and levorotatory. See this, how am I writing? This is carbon, hydrogen, C2H5, and this is your. Now there is one leaving group. I will add Y because X it has to replace its Y. Correct, na? So it is rotating in this direction. Let us name this molecule as A. Same thing, if I am having the molecule in this direction, Y, I should not write C2H5 na, because it should have all 3 different. So this is CH3, this is CH3, this is CH3. Okay, don't mind, this is CH3 because all should be different, right? CH3. Now Y in this direction and hydrogen in this direction. Okay, hydrogen in this direction. So what are you understanding? It can form both dextrorotatory and levorotatory. Yes. So now, so what is there? If A is the only product, if I get only product, then I call retention, because X, wherever X is there, Y it is replacing. This is retention product. If it goes in this way, if it forms this product molecule B, then we call it as inversion. Inversion. Okay. Suppose if this A and B both are forming 50% and 50%, both A and B are 50, then if A and B both are 50%, if A is 50% and B is 50%, then I call this together as a racemic mixture. What do I call? I call this as racemic mixture. Okay, right. So mixture of A and B with 50% concentration is optically inactive. So the racemic mixture, whatever is there, it is optically inactive. Optically inactive. Yes, because as one isomer will rotate the light in one direction, the other will rotate in another direction and it will get cancelled. Easy. So optically isomerism. Careful. I have explained everything. So let us solve a question now. The number of chiral carbons in given molecule is what? Number of chiral. See here. So there are 1 carbon, 2 carbons, 3 carbons, 4 carbons and 5th carbon. Correct na? So careful here. This carbon is 1. This carbon is 1 where it has different groups. This is one group. This is one group. This is one group. This is one group. So the option B is the correct option. So you can draw the structures and elaborate and see it. Easy. So done. Next question. Give reasons of the following. Okay, they are asking you to give reasons. This is how many? 5 questions. So 5 marks answer this is. Okay. So let us write one after the other. First one. Do I have place? No, I need to do this. Okay. Plus and minus. This is racemic mixture. Butan 2-ol is optically inactive. Why? You should write the answer as rotation due to one enantiomer. One enantiomer is cancelled out by another. Cancelled out by another in racemic mixture. That's why it is optically inactive in a racemic mixture. You write this. This is enough for the answer. Don't elaborate. You will not get time. Next, iodoethane is more reactive than chloroethane in SN2. Okay, SN2. First of all, I, when you see I, simple answer, because I is better leaving group than Cl. That's all. Just write group than Cl. Only one line you will write, not expand it, because it is 1 mark. Para-dichlorobenzene is higher melting point than ortho and meta. Simple word, due to symmetry of para isomer, it fits into lattice. It fits into lattice. That's all. Over. Next, 4th one. Haloalkanes easily dissolve in organic solvents. Okay. So basically, polar solvents it will not dissolve because the bond between haloalkanes and haloalkanes is strong. So non-polar solvents or organic solvents they have. Correct na? So what should I understand? New intermolecular interactions between haloalkanes and solvent have the same strength as the ones being broken. Means when the haloalkane dissolves in organic solvent, whatever, when they are dissolving, first of all breaking there between Rx, that means the bond between Rx and the bond formed between the new organic solvent, whatever are there, here both have, or the solvents whatever they are there, both the one which is broken, one which is formed, have same strength. That's why it easily dissolves, breaks and forms. That's why it easily dissolves in the organic solvent. That's what? Yes. In case of water, what did we write? We have written haloalkanes, bond is stronger, we have written. Now Grignard's reagent is stored in moisture proof containers. Moisture proof containers. Why? What happens? Grignard's reagent reacts with water. That's the first thing. Grignard's reagent reacts with water. Reacts with water. Okay, when it reacts with water, what does it form? And forms corresponding alkanes. But we want what? We are adding corresponding alkyl halides we want. That's why it will become alkane. That's why I am storing this in water to prevent it to form alkanes. But the product is alkyl halide, right? Simple answer. Question is here. Answer is here. Over. Easy. Next question. Let us see the next question. Identify and indicate the presence of center of chirality, if any, in the following molecules. How many stereoisomers are possible for these for those containing chiral center? Yes. So they have given 1,2 dichloropropane, 3 bromopropane. Okay, they are asking you identify and indicate the presence of chirality. I have to show the presence of chirality in this. This is a 2 marks question. Okay, so draw the structures. 1,2 dichloropropane. Okay, 1, 2, 3. 1 chlorine, 1 chlorine. See this. This is the chiral carbon. Okay, this is the chiral center because this is CH3 here, this is C here, this is CH2 here. Correct now? All are different. So this is the chiral carbon. Mark it like this. This is 1, 2 dichloropropane. 3 bromopentanone. So 1, 2, 3, 4, 5. Correct. Now this is your bromo. Correct. Pentanone. And this is your asterisk. Now you observe this carbon is the one. This is CH2, this is Br, this is CH2, and this is double bond. That's why this is chiral center. 3 bromo pentanone. That's all. You see. Next question. Careful. Carry out the following conversions: but1ene to butyl iodide, 2 bromopropane to 1 bromopropane. Oh, easiest. Let us do this conversion. That's a rocket. but1ene. First one. First of all, I want what? N-butyl iodide. I want 1, 2, 3, 4 iodide. This I want. From where? but1ene. 1, 2, 3. This is but1ene. Now first of all, double bond means I have to break a bond. Correct na? So I will use mark addition or Markovnikov's addition, anti-mark addition in the presence of peroxide. So what will happen? I can add the bromine atom at the end. Correct na? Highly substitute. I told you no, the H plus ion adds to there. In first case it adds to more number, here to the less number, so you get a bromine. Now easy, I can add sodium iodide and acetone and it's Finkelstein reaction and remove the bromine and I get sodium iodide. That means I get butyl iodide. This is NaBr out. Easy. Next question. 2 bromopropane to 1 bromo. So whenever you see any type of double bond, try to use Markovnikov. So here I want what? 1 bromo. Okay. Propane. 1 bromopropane. Okay. 3 carbons. Now here bromine I have to remove. I can use what? Alcoholic KOH. Why? Alcoholic KOH will try to convert alkyl halides to alkenes. Elimination reaction. Na? Alcoholic KOH helps in elimination. So what do? I break the KBr and I get a double bond. Now to this double bond, if I add, because when bromine is the last, I will simply add HBr in the presence of peroxide. I will do the anti-mark addition and I get a compound. Easy. Very easy, isn't it? Very easy actually. Okay. So next question. Let us see. Out of pentan 2-ol and pentan 3-ol, which is chiral molecule? Pentan 2-ol and pentan 3-ol, which is chiral molecule, they are asking. Okay. How should I do? First of all, pentan 2-ol and pentan 3-ol. Shall we draw the pentan 2-ol first? Okay. Let us write. This is a 1 mark question. Pentan 2-ol. 1, 2, 3, 4. 1, 2, 3, 4, 5. Here hydrogen and there is OH. Okay. Now you only see here. This carbon has CH3 here, CH2 here. So this is already chiral, na? So pentan 2-ol is only chiral. I have already written pentan 2-ol. So why it is all pentan? Pentan 2-ol has chiral center and it is optically, you should write pentan 2-ol is optically active. optically active. Okay, because it contains all 4 different groups, correct, and it exhibits enantiomerism, non-superimposable mirror images, or optic enantiomerism or optical isomerism. It exhibits enantiomerism or optical isomerism. This is what you are going to write. It's all easy. Now next question. The optical rotation of an enantiomer is plus 12.5 degree. Write optical rotation of its mirror image. Second, mixture of enantiomers or mirror images 1:1. Okay, first answer. I have to write for 1, it is rotating towards the right. So the enantiomer to the right direction, it says it is plus 12.5. So now its mirror images will be minus 12.5 degree. That's all now. The right side is sorry, right side is 12.5, so left side is minus 12.5. Correct. Next answer, mixture of enantiomers 1:1. So what will be the rotation? Racemic mixture has 0 rotation. Correct na? Correct. Next question. Sorry for the students, I'm coughing. Anyways, which of the following molecule is optically active? Okay, so for optically active compound, what should it have? It should have a chiral center. That is what I have to remember. Correct na? So it should have a chiral center. That is very important. Optically active compound, chiral center. So chiral center means all 4 groups different. All 4 substituents should be different. Correct na? So check here. Here already 2 are there same. That means this is not. But here 1, 2, 3, all 4. So this is the correct option. Correct na? Because B is optically active. It rotates the plane polarized light because it has chiral center. You see? Next question. Alkyl halide. An alkyl halide is a molecular formula C4H9Cl is optically active. Write its structure. C4H9Cl. Easy na? 1, 2, 3, 4. See, okay, it should be optically active. Okay, that means I have to draw in such a position that all the groups are different. Correct na? Suppose if I draw here, this is CH, this is CH2. Okay, done. All see here. This is a chiral center, optically active. So the structure is this. This is again a 1 mark question. We see next question. Okay, chloroform is stored in dark colored and sealed bottles. Why? Chloroform. Okay, first of all, chloroform, this is again 1 mark question. What happens is, if you don't store it in dark color bottle, it is going to combine with oxygen and it converts into a poisonous gas. This is nothing but phosgene, and your HCl is out. 2 HCl na? Okay, this is 2 HCl. So because what happens? Chloroform, you write chloroform is oxidized in the presence of light to form a poisonous substance called phosgene, a poisonous gas rather, to phosgene. Hence it is stored in dark color bottles and sealed bottles so that it doesn't react with oxygen. Easy? Right, easy. Next question, 1 mark. Why Grignard's reagent should be prepared under anhydrous condition? So what happens, whenever you're using Grignards, we use dry ether, correct na? So what happens is, if you take this Grignard, if you don't prepare under anhydrous, okay, what will happen? It will react with water and immediately it will get converted to hydrocarbon and you will be getting Mg, OH and X. So this is the problem. That's why to get the required product, we use anhydrous condition, that is in the presence of dry ether. Got it? Alright. Next question. Which of the following molecule is chiral? 3 bromobutane, 1 bromobutane, 1 propane, 2 bromopropane. I can directly say 2 bromo. Okay, directly I can see and say. How? Why? Because first one we will write. 1, 2, 3, 4. 2 bromo. Okay. Now see the compound. 2, H and 3. See, all 4 are different. This is CH2, this is H, this is CH3, 4. So the first option only is correct. Over. Correct na? You can write all in C. Only the first option. This is the chiral center, EC. Next question. Which of the following is an optically active compound? Okay. So, wherever if I have to tell you simple two options, second position is there, that will be easy to calculate. Yes, you only see chlorobutane, CH3, CH2, C, your CH3, your Cl and H. Okay, so this is your chiral center, that's why this is optically active. Okay, alright. Next compound, the process of separation of racemic mixture into Dl and S isomers is called what? Resolution, dehydration, revolution, dehydrohalogenation. So the process of separation of racemic mixture or racemic modification is called resolution. Okay. Next, what the major product in the reaction is what? They have given one reaction, so I have to solve what is the major product of this. Okay. First of all, when such reactions are given to you, okay, careful. Don't get tensed. What to do, how to do, nothing. Here we have a bulkier base. Careful. We have a bulkier base. Hence what happens, the base is bulky. Okay. Here there's one thing, U means what? I'll elaborate this answer. Okay. Actually the O minus is nothing but, here let me elaborate. Okay, this is right. This is okay. Now this is on Cl. Okay. Now this is your tertiary butyl oxide. Okay, right? That's the base which I am taking. So what happens when the bulkier base is here, this base. So this comes, first of all, first thing, because of this electronegativity, the bond shifts here. Then this bond shifts here. Then this comes and shifts here. Three things are going to happen. This is E2 elimination reaction. Then what happens? Shift the bond, CH3, then C, then CH3, then double bond, then CH2. What is the name of this compound? This is 2-methyl prop 1-ene. Got it? So this is the reaction. So whenever you see bulkier bases, E2 elimination happens, and you check this and understand. Easy? Easy. And next question, racemic compound has what? Racemic compound has what? Basically, racemic means I know, no? It is 1-to-1 mixture, nothing. 1-to-1 mixture of enantiomers, racemic mixture of equal mixtures of enantiomers. Got it? Okay. Next question. Organic molecule necessarily shows optical activity if, when it shows optical activity, yeah, organic molecule, optical necessarily shows optical activity if it is. So, contains symmetrical carbons, then only it is optical active. It is non-polar, non-superimposable on mirror images, superimposable mirrors. See, optically active compounds are non-superimposable on their mirror images. Option C is the correct one. Correct na? See here what happens, optically active compounds are non-superimposable mirror images of each other. The enantiomers we said na, that's the concept. Okay. Chemical properties of haloarenes. Okay, oh, the last one, almost we are coming closer. So basically your haloarenes undergo, we said no, due to CX bond, because it doesn't show the, what do you say, nucleophilic substitution reactions, correct na? And next thing is not much because of that. So the first concept, before we have 2 pages, okay, I have 3 pages, I will take this. First of all, nucleophilic substitution reactions of haloarenes, if I take, because of the resonance effect and the formation of partial double bond character, resonance effect, which I have explained earlier, what happens? It has, draw all the resonating structures, whatever resonating structures I have drawn earlier, no, all the resonating structures which chlorine getting the CCl double bond, resonating structures, draw it here if they ask you all. And they say it gets partial double bond and it is resonance stabilized. Correct na? Next important thing is hybridization of CX bond. So basically in your haloarenes, the bond whatever is there is sp2 hybridized. The bond is sp2 hybridized. Correct na? sp2 hybridized. That's why what happens in haloalkane, this is in haloarene. Okay, this is in haloarenes. And sp3 in case of haloalkanes. That's why because of sp3 this undergoes your nucleophilic substitution. Here the S character is more, that's why because of the sp2 hybridization it will not prefer, NSR is not preferred much. Easy. Okay, third concept is phenyl carbocation unstabilized, correct now, because I told you, right, when your phenyl carbocation is there, that is unstabilized, instability of phenyl carbocation, I said, correct, because of, see, normally whenever we require NSR we require stable carbocation, but phenyl carbocation, as we have said, it is an unstable phenyl carbocation instability. Because of this instability, what is going to happen is unstabilized, correct now, cation unstabilized by resonance. So because of this it shows certain reactions. What are those? We'll see this now. So here I have one chlorine atom. Okay, one chlorine atom. Okay, now this chlorine atom, suppose the same chlorine I'm going to introduce sodium hydroxide. I'm going to use 623 Kelvin. I'm going to use 300 atmospheres. Okay, so what happens is, because of this, your chlorine is going to get converted into phenol at this temperature. Suppose if I have chlorine, along with chlorine I am having NO2, electron withdrawing group. Now instead of NaOH 623 I am going to supply your 443 Kelvin. Now what will happen? Your chlorine is replaced, the chlorine is replaced by your OH and your NO2. These are your, because of phenyl cation unstabilized by resonance, these reactions are shown. Along with this, your ring also undergoes electrophilic substitution, ESR reactions it undergoes. Yes, in ESR reactions you have different varieties, like Friedel-Crafts first alkylation you have, then Friedel-Crafts alkylation you have, then Friedel-Crafts acylation you have, then nitration you have, correct na? Nitration you have, right? Let us see all those. So first of all, in your chlorine, first thing, you are introducing different electrophiles. This is alkylation. What do you require here? Anhydrous FeCl3. Then you require nitration reaction, where the electrophile here is NO2 plus. This is the electrophile, NO2 plus. Next, you are performing sulfonation. Okay, concentrated sulfuric acid. Here the electrophile is SO3H, where you are heating it. So in this case, first case, you will be getting two products. One is ortho and one is para, where always para product is stable. Ortho and para is stable. In this case, your nitration mixture, same, you will be getting ortho product, but here chlorine is here now. So chlorine is here, chlorine, ortho product. At the same time, you will be getting para product. Ortho product will be getting para product, both, or para is stable. Here in this case, same, you will be getting chlorine, you will be getting ortho product, you will be getting para product. Electrophile. So both are para is stable in this case, correct na? Then Friedel-Crafts reaction. In Friedel-Crafts reaction, you have both alkylation and acylation. Let us draw. In this, both Friedel-Crafts alkylation reaction, what do you have? You have your CH3Cl anhydrous AlCl3. In this case, you have your acetyl chloride, in which term again anhydrous AlCl3. In this case, first case, what will happen? In the first case, you are going to have your CH3 at the ortho position. You also have CH3 at the para position. Para is stable, correct na? In this case, same, you have Cl3, here electrophile is this. Electrophile bonds through CO, and same thing you have para also, it is bonding here. Other than this, you have Woods-Fittig reaction and Fittig reaction, right? Correct. Woods we have already done. Fittig reaction I don't have placed there, so I am writing here. Woods already we did. Woods reaction already done. Woods-Fittig reaction where I am going to take two aryl groups. I am going to take Woods-Fittig reaction means one aryl and one alkyl group. One aryl and one alkyl group will add and do this. So you will get your compound where this plus NaX, 2NaX. So this is Woods-Fittig. Now Fittig reaction means two aryl groups where you get biphenyl. This is Fittig. I am writing here. Sorry for the inconvenience, please, because my handwriting is big, that's why I am not able to fit it in that. Here plus 2Na in the presence of ether, I am going to get two rings, aryl rings, two aryl rings and 2NX. This is Fittig. Okay, Woods reaction is over. Fittig and Woods-Fittig reaction. Is it okay? Now, let us see this question. Okay, so magnesium reacts with RBr. Okay, magnesium reacts with RBr best in what? RBr, it reacts magnesium. So basically what happens, three compounds are given here. Okay, they are used for preparing Grignard's reagent. But diethyl ether is there. This is considered best among all. Why, I'll tell you. What happens is, electron pairs, it has to supply electron pairs to magnesium, correct, for coordination. Here what happens, here there is one ring C6H5, here also there is one more C6H5. So first of all, there what happens, resonance concept, hybridization, that resonance is shifting of pi electrons concept, but here in this case that's not a problem. So what happens is, R, it binds completely to your MX, this is X, this direction it's trying to give electrons to magnesium, here also it's trying to give electrons to magnesium. So what is happening, it donates the electron pairs on oxygen atom, and directly it is sent to magnesium. Here in this case electrons are less available, here in this case less available, that's why your diethyl ether is more preferred. Okay, so what will you write? In case of the B and C option, the electrons are not available, but here in this case the electrons are best available to coordinate with Mg. Is it okay? Next question. 2-bromopentane is heated with potassium ethoxide in ethanol. The major product obtained are 2-bromopentane. Okay, let us see. 2-bromopentane. 1. This is your 2-bromopentane. CH2, CH2, CH3. This is 2-bromopentane. What is it? Potassium ethoxide. Potassium ethoxide. For me, I am taking just the ethoxide part. So what will happen? This is bulkier base. So bulkier base. So what should you remember? Careful. It is going to take or remove the molecule and gets two products. First product is from here. It removes hydrogen. This compound and hydrogen from here. In second case, it removes from here and this. Okay, so I get two different products. First compound is this. Second compound is this. This is, what is this called? Trans-2-pentene. This is major. This is pent 1 ene. This is minor. So trans-alkene, or rather trans and cis, if I have to say trans and cis. So trans and cis, simple. So always trans is more stable than cis. Trans is more stable than cis. So what is the answer? Trans to pentene. So remember, trans is more stable than cis product. Then next question. Alkyl halide reacts with metallic sodium in dry ether. The reaction is called what? Alkyl halide reacts with metallic sodium.
Alright, let's start with the question. Let us read the question first. Okay. When 2-bromobutane reacts with alcoholic KOH, the reaction is called what? Okay, so as soon as alcoholic KOH you see in the question, two things you should remember. First, it is going to undergo elimination reaction, okay, and that's nothing but dehydrohalogenation. It's going to remove your hydrogen and halogenation, and it is also going to form an alkene. This is what you should remember. Let us start the reaction. 2-bromobutane, 1, 2, 3, 4. Butane means 4 carbons. Bromo means second carbon. Now CH3, your hydrogen, H2, your H3, correct? Now what you're doing, you're going to use alcoholic KOH. Don't take aqueous. It is not aqueous. Aqueous is no, it is alcoholic. Aqueous undergoes nucleophilic substitution, and this undergoes elimination. So hydrogen from here and bromine from here, it removes, and the bond which is here just goes and adds. So what do you get? You will be getting an alkene. Alkene, correct? Na? So this is your compound. So what is the name of this reaction? This is called dehydrohalogenation reaction, because I am removing here hydrohalogenation. Hydrogen is removed, halogenation is removed, and you get the product. Okay, easy. Next question. Let's go to the next question. An alkyl, this my writing pad is a little bit bothering me, but anyways, okay. So an alkyl halide by formation of Grignard's reagent. Okay, let us read again. An alkyl halide by formation of its Grignard reagent and heating with water yields propane. Okay, it's NCERT page number 311. What is the original alkyl halide? What did they say? An alkyl halide by formation of its Grignard's reagent with water yields propane isomers. Okay, that means they said we don't know the alkyl halide, but it is going to form propane isomers. Propane, this is what it forms. Okay, now they also said it undergoes hydrolysis, so I have to go back. Propane is a final product. Go back with your original propane alkyl halide, and you are going to add your bromine. That is how addition and then hydrolysis goes, na? Okay, then what should I add first? I have to add magnesium metal. Then it forms an additive product CH3 CH2 CH2 MgBr. Now this is your Grignard's reagent. Now you take that Grignard's reagent, and now you are going to do your hydrolysis to this Grignard's reagent. Hydrolysis to your Grignard's reagent. Then what happens? The bond breaks here. Yes, hydrogen comes and attacks here. Magnesium bromine goes out with this, and you will be getting MgOH-Br. That's all. So propane is ready, and the alkyl halide is this. So what is the alkyl halide? They asked. They said the alkyl halide is propyl bromide. That means to get propane, you will use propyl bromide. To get butane, you will use butyl halide or butyl iodide or bromide, whatever it is. Easy? Very easy question. So next question, let's see. An organic compound. So an organic compound, this one, my writing pattern, it's like little, its brain has become little bit loose. Okay. So an alkyl halide or an organic compound, this one, the formula is C4H9Cl. On reaction with sodium or diethyl ether, it gives a hydrocarbon which on monochlorination gives only one chloro derivative. What is A? That is what they asked. What is A? Let us understand carefully. The compound is C4H9Cl. Okay. That on reaction with sodium diethyl ether, it gives a hydrocarbon, which on monochlorination gives only one chloro derivative. Okay, only one chloro derivative it should give means it will form a compound, means the chlorine is in the terminal carbon part. Okay, let us take. So C4H9Cl. What is C4H9Cl? Okay, one carbon, 2, 3, 4 Cl. Okay, I took a carbon with this is C4 na. So C4. Okay, 3 and 4. This is your C4H9 369. So what is this? This is nothing but tertiary butyl chloride. Tertiary butyl chloride. This is okay. Okay. Now what did I do? I am adding 2 because sodium diethyl ether is nothing but your reaction with sodium metal. That's nothing but Woods reaction na? Yes, Woods reaction. So Woods reaction means I have to take one more molecule of this, one more molecule of this, one more molecule. Then what will happen? This Na will comes out and you will be getting, so Woods reaction I think I will write here. This is Woods reaction and you will be getting a big compound. What is that compound? I am writing it here, students, because it will cover. So this is your CH3. I am writing this one here. CH3. This is your CH3. Then C. This is your CH3. This is your CH3. This is your CH3. Okay. Now they said it forms only one chloro derivative. Okay. So I am going to take chlorine monochlorination. So shall I write monochlorination? Monochlorination. Only one chlorine is going to replace itself. Which one it will replace? It will replace this terminal one. So I am going to get CH3, C, again one more C. There is one more CH3, one more CH3, one more CH3, here again CH3 and your terminal. So this is your monochlorinated compound. Now what is this? So they have given option A, tertiary butyl chloride, secondary butyl chloride, isobutyl chloride, N-butyl chloride. Easy na? This is a tertiary compound. So it is tertiary butyl chloride. That means what clue you should get? To get monochloro derivative, you should take the double, whatever compound is there na. So that one you take it as tertiary. It will become double. See here, it has become double na. So tertiary butyl chloride. Don't take isobutyl or something. It will bother you. You'll get a wrong answer. So this is irritating again. Okay, all right. So I think some problem with the writing pad. No, actually I was not using since long na. So it's little bit okay. Okay, now it's fine. So next question. The major product of the following reaction is what? So the major product, okay. They have given one compound, okay, then sodium ether, then bromine in the presence of H nu, then C2H5O and ethanol and heat. Okay, nothing, students, it's easy. Don't panic when you see this compound. What is this? Sodium and ether. So what does it do? So basically your sodium and ether, now they've given your heterocyclic compounds. So seeing that maximum students panic, I'll do that for you. Just check how am I doing it. Now 1, 2, 3, 4 bond, now Cl and Br. Now when I add sodium in the presence of dry ether, it's going to remove that and it's going to form a cyclic compound in this way. Okay, cyclic compound with a substituent. And further, because I need to find the options which are there in this, correct? Now I need to find an options which are there in this. So while I'm going, because I need to find some compound which is matching this formula. So how many carbons are there? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So fifth 5. This is also 5. This is also 5. So careful. Okay, between these two I need to check. Then bromine in the presence of H nu. So your halogenation, free radical reaction. So okay, I should not take that. So bromine, one here, one bond here, and one bond there. This is okay. Then they said bromine H nu. After that, I have introduced C2H5O in the presence of ethanol, and you're heating it. Okay, now what happens? That removes the brominated molecule from there and you will be getting one compound
and the bond shifts here. The double bond shifts here, removing the bromine, and you'll be getting. So what is this compound? And there is a formation of So what is this compound? The compound B is the correct option. Correct na? Okay, easy. Next question. Okay, ma'am, these are all difficult. No, they are not difficult actually. It seems to be difficult, but it is easy. Now see here. Forget about the ring. Ma'am, the heterocyclic compounds, I don't know. You just concentrate on your reagents. Okay, this is what is important. Now, what did they give me? Do I have place? I have place. Okay, first what will I do? I have one page. Okay. First take this compound. First one, I'll write the question. Okay, the question goes like this. Okay, easy. It is your bromine is here, your chlorine is here. What did they introduce? They have introduced magnesium in the presence of ether. Correct na? So what will you do? You will add this to, let it be heterocyclic, let it be anything. And the shape of the molecule is bad, but please don't mind because I'm writing with my pen. Now, just like a water hydrolysis we do, here we are doing with deuterium oxide. Nothing. What the deuterium oxide does is, it goes and attaches to your, instead of this, your chlorine, and what will happen to this Mg? There, what did we do? MgOH Br. So here Mg, your OD-Br will come out. Then next, what did they do? They introduce sodium in the presence of ether. Sodium in the presence of dry ether is what? It is Fittig reaction, because two molecules, because sodium ether, two sodiums I'll introduce. So the one more molecule you will add. So indirectly, that means you are adding one more molecule to this. It is something like this. One more chlorine and one more D is here. So what will happen? Two Na is there, right? Na will pull out that NaCl. Two sodiums will pull out 2 NaCl, and I will be getting a compound. It's easy actually. The concept is easy. If you know the concept, it is done. Organic chemistry concept is important. That's all. So option, this is your compound. So which molecule is this? Which molecule is this? Yes, this is your answer. Easy? Easy. Very easy question. Let us see the next question. Bigger question. A dihalogen derivative X of a hydrocarbon with 3 carbon atom reacts with alcoholic KOH and produces another hydrocarbon which forms a red precipitate with ammonical copper chloride. X gives an aldehyde on reaction with aqueous KOH. The compound X is what? Nothing. Easy question. First of all, a dihalogen or derivative X of a hydrocarbon, they said. Dihalogen derivative of a hydrocarbon means there are 2 chlorine atoms in a hydrocarbon chain. Okay, 2 chlorine atoms hydrocarbon chain with 3 carbon atoms, they said. Okay, 3 carbon atoms means what? 1 CH3, CH2, CH2, Cl2. That's all. But here chlorines are 2 means this becomes only H. What is this? This is 1,1 dichloropropane. 1,1 dichloropropane. This one is what is X. What do they say? This, do I have place in the next? No, I don't have. I should do it here away. What does this do? This is going to react with your alcoholic KOH. Done. So what will alcoholic KOH do? It will do your elimination reaction. And they also said, okay, let us do this alcoholic KOH. So what will it do? It will take out dehydrohalogenation reaction. So, and forms an alkene. Now in this case, what will happen? Let us see. It is going to remove 2 chlorine atoms. So two double bonds you will get. CH3, C means these 2 chlorine atoms I should remove, means 2 hydrogens I have to remove from here. C triple bond CH. This is your hydrocarbon. Okay, hydrocarbon. Along with this, you will also be getting KCl. You will be getting water also in this case, 2 KCl. Now they said alcoholic KOH and it produces another hydrocarbon. This is one more hydrocarbon which forms a red precipitate with ammonical copper chloride. Okay, so let us take that. I am pulling that arrow here. It's going to react with what? Ammonical copper chloride. Okay, ammonical copper chloride is which reagent, students? Tell me, is it Tollens reagent or Fehling solution? Okay, Tollens or Fehling's, please tell me in the comment section. So this is going to react, and what will it do? It will form a red PPT, they said. So I will just write red PPT, no problem. Red PPT is what they said. They didn't ask me which compound. Now they said this X, whatever is there, it is going to react with aqueous KOH. Aqueous KOH means hydrolysis, na? Okay, and they also gave aqueous KOH and gives an aldehyde, they said. Which aldehyde? How many ever carbon atoms? That aldehyde only, na? 3 carbon atoms. So I'll be getting the required aldehyde. That's all. This is your aldehyde. Now what is the question now? What did they ask me? What is the compound X? They said. Oh, simple. The X compound is 1,1-dichloropropane. Easy? Very easy question. Okay, now next question, ma'am. It is difficult. No, it is not difficult. It is easy. The structures may scare you. Just see. The major product of this reaction, they've given this. HBr is given, and pH is nothing but your C6H5 they've given here. And what is P? What is the product for? First of all, HBr is given. Is there any peroxide given to you? Sorry. Is there any peroxide given to you? No, they have not given peroxide. That means I have to do Markovnikov of addition or anti-Mark addition. Mark addition is what I have to do. Okay, solution. Let us take, this is your pH. I am copying the question again. This is your bromine. Okay, now I am adding what? I am adding HBr. Okay, so what addition you going to do? HBr. Okay, so I said I didn't say anything. Mark, I didn't do, I have not written any peroxide. So this goes and adds here. Okay, then this is your pH. The bond breaks and you will be getting a product of this, and this is your carbocation. Correct. Now what is this? This is stable carbocation, but this is phenyl carbocation. Right? This is associated with the phenyl ring, C6H5. So what will happen? Stable carbocation due to delocalization with phenyl ring. This is very stable carbocation delocalization with phenyl ring. So what will happen? You are going to introduce, now they said HBr only. Okay, you will introduce one more nucleophile into this, so that that positive charge is occupied and it satisfies there, and your Br. Easy. This is a compound, nothing. You get confused. So what is the answer for us? Answer is C, na? C only? C6H5, yes. See here. This is one bromine here, this is one bromine here, and this is a phenyl ring. That's it. See? Next question. What is true about the stereochemistry of the products formed in the reaction? What is true? Okay, stereochemistry, it seems the chiral carbon is given. This is different, this is different, this is different. This is okay. What are you observing? In the first structure, molecule is, this is same, this is same, this is also same, this is also same. Here, instead of CH3, there is a formation of CH2Cl. Okay. So they said stereochemistry means you will talk in terms of what? Chiral carbon. Talk in terms of chiral center only. That only is stereochemistry. So what answer? Let us understand. Here, is there any bond broken at the chiral center? Okay, first thing understand. No bond is broken. No bond in chiral center is broken. Okay, chiral center is broken. There is no bond which is broken here. Okay, then what will happen if the bond is not broken? Configuration of the reactant is maintained. Na? See this? Only addition is there. See, this is intact like this. So configuration, the complete configuration. See the structures, the whole structure, the configuration of the reactant is retained. Reactant is retained. It is like that only. Correct, na? So what is the answer here? So what happens? What is true? Racemized product I got, a retained product, or inverted product, or more inverted? No, it is a retained product when I see the structure of this. Correct, na? Okay, next question. Aminolysis of alkyl halide followed by the treatment with sodium hydroxide can be used to prepare primary, secondary and tertiary amines. The purpose of sodium hydroxide in the reaction. Oh, Now what is this amines question? They have given nothing. I'll tell you, because alkyl halide aminolysis na. So what did they say? First of all, aminolysis means addition of ammonia to RX. First of all, let us take one alkyl halide. I am taking one alkyl halide. Now what am I doing? I am adding ammonia to this. When I add ammonia to this, what will happen? The particular whatever ammonia is there, it's going to combine with the alkyl halide and it is going to form RNH3 plus and your halogen X minus is out, right? So during aminolysis, what will happen? The acid, whatever acid liberated during the reaction, whatever is there, it is going to combine because it's treated. It combines with the amine, whatever is there, it combines and forms amine salt. Now what is this? This is an amine salt, correct na? So amine salt, because this is the base and this is the acid, it becomes amine salt. Now to take that amine salt, okay, a base is needed na. So what will I do? I'll take that amine salt. Now I add one base to this. So what will happen? Water comes out, I get amine plus water. So what is happening here? Each substitution whenever I am doing, okay, acid concentration is increasing in the reaction mixture, correct? Acid concentration is increasing in the reaction mixture. So to remove acidity or acidic impurities, what has happened? Sodium hydroxide is added, correct na? See here, as a salt, it is increasing, salt formation is happening. Here acid is liberated. Again I am adding, this is becoming salt. Again to take out, I am adding base. So every time whenever you are adding sodium hydroxide, what are you trying to do? You are removing acidic impurities, correct na? The acidic impurities are removed from this. Now where is this acid here? Check again. During aminolysis, the acid liberated during the reaction, this is your, see, just take your conjugate acid and base, okay? So that acid, to neutralize that, I took a base, okay? Chalo, next question. Chlorobenzene reacts with magnesium in dry ether, gives a compound A which further reacts with ethanol to yield water. Okay, so they said chlorobenzene. Okay, so let's see. Chlorobenzene C6H5Cl. It is reacting with magnesium. Magnesium in dry ether. Okay. What do I get? C6H5MgCl. Okay. Then further reacts with ethanol, Ca2H5OH. Simple, easy. First thing, always remember whenever you're adding hydrolysis or deuterium oxide C2H5, the bond breaks here where the hydrogen, careful, this ozone adds and the compound becomes benzene plus your C2H5O MgCl. This is what forms. Easy. So what is the correct answer now? B. Benzene. Chlorobenzene means benzene. Okay. Next question. Benzene reacts with N-propyl chloride in the presence of anhydrous AlCl3. So anhydrous AlCl3, they said, I'll just pull my table a little bit ahead. Okay. Yes. What is the compound? N-propyl chloride. Okay. A benzene reacts. It reacts with N-propyl chloride, means a normal propyl chloride, terminal chloride. It reacts with anhydrous AlCl3. So what will happen? This is anhydrous AlCl3, loose acid, correct? So your benzene molecule, it reacts and it forms, the molecule goes and adds and you get this compound. What is this compound called? This is one hydrogen, so this is isopropyl benzene. Isopropyl benzene. Is it okay? Next question. Okay. Oh, scary? No, don't worry. It is not scary, but it is a bulkier solvent, bulkier base rather. Okay. So the major product of the following reaction. Do I have place? I don't have place. I have to solve here. So first of all, let us take this. This molecule is okay. Let me draw the question. Okay, so you're using tertiary butyl hydroxide and heat. It's bulky. So during this, what happens? First of all, there is shift of the, now you have this, correct na, tertiary. This reaction is even reaction, even elimination one reaction. Okay, so ma'am, we don't have even, I'm using this for your NCRT page 309. This question is there. That's the reason we have used this positive charge. So what happens is, you're introducing the hydrogen from here. There is shift of hydrogen. That's nothing but 1 to shift, 1 to hydrogen shift. So 1 to hydrogen shift. Then what happens when once the hydrogen molecule shifts? Careful, let me do this. Then I will explain. Okay. Okay. So the hydrogen, once it is shifted from here, it's going to shift here, and then finally minus H plus. Then you will get this bond and it will become an alkene. It becomes an alkene. Okay, right. Okay, now what is this? In even elimination reaction, you observe 1 to hydrogen shift. Once 1 to hydrogen shift is observed, the bond shifts from there and it converts into your alkene molecule. So the major product formed here is nothing but this compound na. Check here. This is your double bond. Okay, it's like this. This is a double bond, and okay, this resembles compound C. Correct na? Okay, so whenever there is bulkier groups like this, remember you have to do the elimination reactions getting an alkene. Okay, next. Which one of the following is most reactive towards nucleophilic substitution reactions? Okay, NCRT page number 304. Now, this is alkene, benzyl. Okay, it's C6H5Cl. Okay, then this is also alkene. This is also alkene. So they said SN1 or SN2. They didn't say, correct na? So first thing what you should remember is, more the stability of the carbocation, more the stability of the carbocation. Remember, higher will be the reactivity. Higher will be the reactivity. Okay, reactivity of parent chloride. Higher will be the reactivity of the parent chloride. Now, first of all, one is allyl, one is vinyl, one is chlorobenzene. Correct na? Correct. Allyl, vinyl, we have already studied if it is directly attached, if it is indirectly attached. So the order is always allyl comes first, allyl chloride, then comes your vinyl chloride. This is order of stability. Then comes your chlorobenzene, whatever is a chlorobenzene. Now tell me here, what is the allyl chloride here? This one. So this is your allyl, because your chlorine is attached to a carbon, then you have a double bond. This is vinyl, because here it is directly attached to this double bond. Correct na? Yes. So compare. So D is the correct option for this. Shall check next question. This is a compound. They asked, this particular compound obtained by chlorination of N-butane will be what? Chlorination of N-butane. Okay, how to do this? Chlorination. First of all, for the chlorination, let us first get a free radical. I am going to get a free radical. Okay, one free radical. What does this do? It will go and attack this molecule. They said this molecule is obtained by chlorination of N-butane, they said. So let me take one N-butane. Okay. CH2, I took one butane. Then what did I do? I introduced chlorine and HNO. So what will happen? This chlorine, the molecule, because of the halogenation, so what will happen? It may attack on either side. It can attack this side, it can attack that side. So when it attacks the butane molecule, you will get two varieties of products. How? I am writing here. First product and second product. Check here. One carbon, CH3, hydrogen, Cl and C2H5. This is one variety. So what happened here? it has gone in this direction. So this is derotatory. Correct? Now D form. This is D form. Same thing. Chlorine on this side. Count the number of carbons and hydrogens. It will be same. Hydrogen. This is C2H5. C2H5. Now here the chlorine atom is in this direction. So this is L form. So now what happened? D form and L form both are formed. This is 50%. This is also 50%. Correct na? So what is this? This is nothing but the racemic mixture. Racemic mixture of both. Correct? So they said you have a compound formed in this direction. This one. That's the same compound I took. Obtained by the chlorination of what? It's formed by the chlorination of racemic mixture. Because it has attacked from both the sides. Is it easy? Easy question. Next one. The number of possible enantiomeric pairs that can be produced during monochlorination of 2-methyl-butane. Okay, monochlorination of 2-methyl-butane. How many enantiomeric pairs they are asking? What are enantiomers? Enantiomers are... Okay, let us first do. First, draw all the possible monochlorinated products of 2-methyl-butane. First draw. 2-methyl-butane, first one I am drawing. Enantiomers means it should have a chiral center. Careful. Okay. This is how you should do. First, what will I do? Butane. Na? 1, 2, 3, 4. And I will make this. Now I will add chlorine to this. Now let us see this hydrogens. This is H2. This is H. Now is this chiral center? This is chiral center. One hydrogen. CH2. This is one CH2. Okay. This is one chlorine. This is CH2. This carbon, careful. 1, 2, 3. Shall we make hydrogen CH3? Okay. So 1, 2, 3. Ma'am, these two are same, na? Okay. Well, let us do one more thing. Let me take an eraser. Sorry. I will take an eraser. 1 second, students. Little confusion. Okay. 1 second. Sorry. Okay. Chalo. Let us again analyze it. I have to draw a first structure with, first I'll make chlorine. Then I'll do CH2. Then I will take CH3. Then CH. Then now this is correct. Yes. So is this not chiral center? See this? All it has hydrogen on this side, CH3 on this side, CH2 on this side. So this is first monochlorinated compound because it has all 4 different groups. This is optically active over first one. Now this is your first one. Second one. Your CH3, then C, then your CH3, then CH2, then CH3. Now this is your chlorine. Now what happens here? Here in this case, CH3 and CH3 both are similar. So this is optically inactive. Optically inactive. Okay, done. Now let us draw the third one and see. How can I shift? I will take this. Okay. Okay, yes. Now I shifted little chlorine to the next adjacent carbon. Now see this chlorine is attached. This carbon is attached to chlorine. It is attached to CH3. This is again attached to CH. Then it is again attached to CH3. Correct na? So this is optically active. Optically active. Let us write the fourth one in this case. 3 C CH3. Your CH, CH2, CH2, Cl. Okay. Now what happened? Chlorine attached to 2 hydrogen atoms. This is optically inactive. Because all 4 should be different. Na? So structures 1 and structures 3 has 1 chiral carbon. So these two can form enantiomeric pairs. So total, what did they ask? Number of possible enantiomeric pairs. How many are there? Total, there are 2 enantiomeric pairs. Okay. So simple. So 2-methyl-butane has 2 enantiomeric pairs. These two are optically inactive because they have same atoms around. Okay. Next important points you should remember, students. This is very important because like haloarenes, whenever you are doing, try to revise all these points. because they may ask you this question as a 5 marks question. So 5 marks question, careful with this. Okay, chalo. We have already discussed this. Let us proceed. Consider the following bromides. Okay, so arrange the following in the correct order of SN1 reactivity. SN1, no problem. First of all, SN1, okay, I'll do one thing. This question, I'll leave it to you all. Will you all try and tell me, or shall I explain? No, you all don't have time, na? I will only do it. So SN1, basically, what is the reactivity? It requires bulky groups or less bulky. It requires tertiary, secondary, primary, and methyl. I thought I will do it. I will give it to you, but it's okay. You're all busy. Methyl halide. This is the reactivity. Now, among all these, let us first analyze. So A, B, C are there. In this case, when this bond breaks, what do you get? You get a positive plus bromine. This is one, correct na? So ionization when you do. Now in this case, if you do double bond, you get a positive charge and this. Okay, this bond shifts here. Okay, this is your secondary. Now in this case, when you take it bromine, and here you will get a positive charge. Okay, now this is which carbocation? This is secondary carbocation, correct na? This is which carbocation? This is also secondary carbocation. Okay, this is also secondary carbocation. Now tell me this, what is the difference between this and this? This has double bond. So this secondary carbocation is resonance stabilized, correct na? It is resonance stabilized. But in this case, is there any resonance? There is no resonance, correct na? So always remember, SN1 reactions, they involve formation of carbocation as an intermediate, correct, in the rate determined step. So the stability of carbocation is most important. Because of the stability of carbocation only we are taking this. So you tell me, among these two, which is more preferred? So the stability of carbocation, though the order is this, I should remember that always whichever is resonance stabilized is most preferred in SN1, most preferred, correct na? So first comes your B option, B, wherever you're seeing resonance stabilized. Then comes your C option because it is secondary. Then comes your A, that is the last one, correct na? Yes, this is your this is your primary. Okay, so primary is last. So always remember, go with the resonance stabilization concept. Easy. Next question. Consider the following reactions. This is the reaction. Okay, the mechanisms of the reactions 1 and 2 are respectively what? This is one reaction. Okay, the mechanism, this is a nucleophile. Okay, and this nucleophile is strong nucleophile. Okay, right. And then this is used as a solvent in this case. Now I remember, this is a solvent in this case. Then okay, so careful. What should I understand here is, first thing is, for SN1 reaction and SN2 reactions, carefully observe the solvent, because in SN2 reaction you require strong nucleophile. Okay, SN1 you require a weak nucleophile. Ma'am, how do I know the order of nucleophiles? You have nucleophile order in coordination compounds, check that. Next, here in the first reaction, C2H5OH is used as a solvent and it is a weak nucleophile. Say this, okay, C2H5OH is used as a solvent and it's a weak nucleophile. This one is a strong nucleophile. Remember, this is a weak nucleophile, this is a strong nucleophile. Go and check in the coordination compounds, you have nucleophile order. So weak nucleophile is favored by SN1 reaction, strong nucleophile by SN2 reaction. Okay, easy. So go, please study the order of nucleophiles, very important for your SN1 and SN2. So what is the question now? It is SN1 and SN2 reactions. Okay, next, for which solvent rate of SN2 will be maximum? Where SN2 will be maximum, for which solvent they are asking. So I said na, again SN1 and SN2. Careful, this SN2 always requires polar aprotic solvents. SN1 requires polar protic solvents. Okay, so here, for which solvent rate of SN2 will be maximum? Now these are all the solvents. Now you check which one is, this is polar SN2 aprotic, means there should not be any formation of H plus ions, the OH minus ions. Alright, so this is 100% acetone. Okay, doesn't form any H or OH minus ions, right? So this is SN2 preferred maximum, because polar aprotic solvents, and proton, there is no proton, H plus ion is not there. So 100% acetone, that's the option for this. Next question, increasing order of reactivity of the following compounds of SN1 substitution. Okay, ma'am, what is this? It's scary? No, it's not scary. SN1 means, always remember, careful, SN1 order is always same. What is SN1 order? SN1 order, you have to remember, it depends upon stability of carbocation. 3 degree greater than 2 degree greater than 1 degree greater than methyl group, methyl halide. Now in this case you check na, which one, which is primary, which is secondary, which is tertiary. You can easily see. Now there are a lot of things what to do. Don't panic, first understand carefully. In the first case, okay, A case, what happens here? In the A case, when the bond breaks, it forms a carbocation. It forms a carbocation in the A case. So what carbocation it forms? 3 alkyl groups are there. 3 alkyl groups means this forms tertiary carbocation. Okay, next, let us go with B part. B, when it cleaves, what will happen? It will become primary carbocation. Now break this bond now. So when the bond breaks, cleaves here, okay, the CH2 bond, whatever is there here na, so chlorine goes and you will get CH2 plus here. Okay, this CH2 plus, okay, right. Then when I cleave this, here also CH2 plus. Now what is the difference between this and this? Here carbocation, both the case, this carbocation is more stable compared to this. What is the reason? In this case you are able to see there is plus I effect of which one? This molecule. Plus I effect of OCH3 group keeps on releasing. Yeah. Now because of this plus I effect, what will happen? The compound, the molecule is more and more stable. The carbocation is more stable compared to this. Now come to the conclusion. SN1 reaction, we said it is tertiary, secondary, primary and CH3X. Now among all of this, what is the first, which will have maximum? C part. Because of which group? Plus I effect of OCH3, which is stabilizing the carbocation. Plus I effect will stabilize the carbocation, correct na? Then comes your D part, correct? Then comes your A part, because it is least preferred. Then comes your B part. Okay, ma'am, why compare to these two? See this is tertiary, this is primary. See, as we proceed, can we just check once again? Correct order, C is greater. Okay, Okay. Alright. So I have a doubt now. B is less compared to A. Okay. B is less because this is primary. This is tertiary. Primary is always less, na? Then this is tertiary. Then this is resonance stabilized. And this is compulsory. Finally, it is completely stabilized. Okay. Option this is right, students. Because again I am mentioning B subsequent because it is primary. Then comes A, it is tertiary. Then your this is resonance stabilized to the last one. That's why because of the plus I effect. Okay, that's clear. Okay. Next question. Which of the following compounds will show retention in configuration on nucleophilic substitution by OH minus? Which one will show retention? They are asking. Okay. So first of all, inversion in configuration. Okay. Which molecule they are asking, na? Okay. So first of all, let us first understand. Inversion of configuration is there, then only retention, na? Correct, na? After inverting, then it undergoes retention when the nucleophile can attack. So when will this inversion happen? This inversion will happen when the nucleophile attacks, but at stereogenic carbon. Correct, na? That is what we studied. So when the nucleophile attacks, then the retention of configuration takes place. Now this one is which reaction? SN2 reaction. Correct, na? So just observe carefully. Among all these, I am going to take the stereogenic carbon. Here no, here no, here no, here no. Yes, this is different. Now check here. Bromine is attached to. Okay. Now let me try once. I have placed. CH3. Okay. Carbon. Let me check because the hydrogens how it is differing, because I want a stereogenic center, na? So hydrogen. One more is a rare end. It is C2H5. Then your C. Then two hydrogens are here. I am just checking once. This is your bromine. Okay. Now what did they say? OH minus is attacked. Substituting OH minus. Let me check one and then see. So SN2 reaction. So what is happening? Your bromine and your OH is replaced. Correct, na? This goes and replaces in this direction. So CH3, C, hydrogen, C2H5, C, hydrogen, H and H. Okay. Alright. Now, they said in which of the following compounds will show retention in configuration of nucleophilic substitution? As I said, for inversion in configuration, I am writing something important. Inversion of configuration takes place. Configuration takes place at which carbon? At the carbon in which nucleophile attacks, but at the stereogenic center, stereogenic carbon. So then what will happen? Your retention of configuration takes place. Okay, that's the reason, because of the stereogenic carbon, I have chosen the last option of this. Okay, chala. Next question. That's all. Oh, one more question. This is a blank page, students. Blank. Okay. The best way to convert CH3F into CH3OH. Okay. CH3F to CH3OH. What is this? Okay, how to understand this? First of all, this is also a nucleophile. This is a nucleophile, na? Okay. So, first concept is CH3F. Here, F is not a good leaving group. It is not at all a good leaving, highly electronegative, na? Not a good leaving group. Okay, first. Now, and next thing is, they said convert RF to ROH. So I have to first treat it RF. I have to treat it with NaI. Then this will become Ri. correct na, because NaF will come out. After that Ri, this is a good base now, good base. Then what will I do? I will treat this Ri with NaOH, so I'll get ROH. This ROH, now what will happen here? I is a good base as well as good leaving group also, so I'll get ROH, correct now. So how to convert? How will I convert now? Okay, this actually question problem here is, students, this part na, this question, this one, this one is the next question part. I was wondering why this is here. Sorry, this is next question clue. Okay, sorry, this should come there. Sorry for the inconvenience. So the question till here only. So next question clue. So that is there na. So option B is the correct one. Sorry for the inconvenience. All right, next question. The decreasing order of reactivity towards dehydrohalogenation E1 reaction of the following is. Decreasing order of reactivity. Okay, so first of all, always remember E1 reaction, unimolecular reaction. What steps are involved? 2 pages I have. I will explain you then. So first of all, E1 mechanism, whenever somebody is talking, first important thing is formation of carbocation. Okay, this is very important. Formation of carbocation. This is your rate determining step, RDS. So in this case, whatever is there, chlorine is there na. So chlorine leaves and it generates a carbocation. This is first step. Second one, rearrangement. If rearrangement is required na, if it is needed, rearrangement will happen. If needed, rearrangement will happen. So in this case, for a more stable carbocation, what will happen? They should either have a hydride shift or an alkyl shift for a stable carbocation. This will happen in step 2, hydride shift or alkyl shift. It may occur. Third step, elimination will happen. Elimination of proton will happen. So whatever base is there, or the base, what it does, I'm just giving you the general steps. Base removes the proton from adjacent carbon. When it removes, what will happen? It will form a double bond. Base removes and it forms a double bond. Okay. Now, understanding all this, what is the order in even reaction? The order is allylic / benzylic / 3 degree, means slash, no, oh, sorry, it is not slash. I will take out eraser. 3 degree greater than 2 degree greater than 1 degree greater than methyl. Okay, these are the steps. Okay, right. Now let us go to the question. Now they have given option 1. What is this? This is 1-chlorobutane. So what will it form? It will form 1 degree carbocation. Next, this is 3-chlorobutane. What is it? There is one carbon atom in between. So this is allyl carbocation. Next, this is secondary carbocation, and this one is tertiary allylic carbocation. Correct na? Now see the order. What did we write? We have written an order, that is, first comes allylic, then benzylic, tertiary, secondary, 1 degree, and methyl. Now you tell me, among all those, first one, what does it come? Yes, first comes your allylic. So allylic, what is the allylic carbocation which we have? We have written the carbocation, right? So first your D comes, D. Then allylic. Then comes your D is tertiary allylic. Okay. Then comes your B. After that comes your secondary C. Then comes your 1. So D, B, C and A. You see? Okay, next question. Okay, that's all. Oh, there's one more question. Okay, right, let us see this. Arrange the following in the increasing order of reactivity towards nitration reaction. Nitration, the nitrating mixture is HNO3 and sulfuric acid. Here the electrophile which is formed is your NO2 plus. Okay, so first of all, nitration, para-xylene. Okay, let us write all. This is your xylene molecule. Okay, then comes your bromobenzene. This is your bromobenzene. Then comes your this is a mistylene molecule. Okay, this is your 3 alkyl groups is mistylene molecule. Then you have your nitrobenzene. Then you have your benzene molecule. Correct na? Yes. So next important thing what you should understand is increasing order of reactivity towards nitration. In all these cases, point to note is NO2 group is an electron withdrawing group. Your alkyl groups are electron releasing groups. If your electron withdrawing group is present, it will deactivate the ring. Deactivates the ring. It makes the ring weak. So it will try to pull the electron density. So when this is pulling, this will become minus and the benzene ring becomes positive. So then what will happen? Automatically the electrophile whatever or there, the NO2 group nitration, will it go and attack? This has become all electrons and this has become positive. This is positive, electrophile also is positive. Will it go and attack? No. Correct na? When this is dragging, this will get the electron density. This will become the positive charge. This positive and this positive, will it attack? No. But when you have electron releasing groups, yes, automatically it keeps on releasing and the electrophile comes and attacks because it will go and take the nucleus, it will pull the electrons. Na? That means always remember, careful, your electron withdrawing groups are there, means don't go with that. Go with electron releasing groups. So the first option would be which has more, सबसे ज़्यादा C part. Correct na? Mistylene has more. So the least one will be D. Electron withdrawing group will have less. Then comes your B part, electronegative atom. Then comes your E part, resonance stabilized. Then comes your A part, only 2. Then comes your C part, because C part has lot of electron releasing groups na. So that which has electron releasing groups, electrophile will go and crave for that. Okay. Yes. Understand the question? Next question. Almost I think we are almost able to complete. Let us see. Okay, I think 3-4 questions, students. I think almost. Yes, polyhalogen compounds are also there. Okay, what I'll do is I'll finish 2 more questions and then we will take a break. Okay, we'll do this and we'll take a break. Order of reactivity in SN1 reaction is what? SN1 reaction, order of reactivity. Okay. In SN1, what is the order? I first require always carbocation strongest stability. Whichever is more stable carbocation, I want that. Okay, I require most stable carbocation. I'll prefer this. Then, okay, let me go back and understand. First thing, option 1. This is which carbocation? Yes, benzyl carbocation. Okay. Which is this? This is allylic. Correct na? This is allylic. This is also allylic. Okay, now 1 minute. Second part is Carbocation stabilized with lone pair of electrons. Okay. Here carbocation with lone pairs. Okay. Third one, this is allylic. Fourth one, this is also stabilized, this is also stabilized. Okay. Let us take case 1 is benzylic. Okay, then carbocation. Okay, now understood. So the fourth one is this is extended allylic. Extended allylic. Okay. Now careful, as I have told you, always remember SN1 reaction, case 1. Observe carefully. First important thing in all these which I have taken. Second one is the most reactive. Why? It has strongest stabilization. I will write. Second molecule is most reactive. Why? Because the carbocation is stabilized. Carbocation is stabilized. Okay. By oxygen lone pairs. By oxygen lone pairs. Now, when I go with the fourth one, what will happen? It has extended allylic group. Allylic. So extended allylic will have, this is also resonance stabilized. Next, third one, that is allylic carbocation. Allylic carbocation. What will happen? Moderate resonance. Moderate resonance. Fourth one, not fourth one, first one. First one is least reactive. Least reactive. So this is benzylic carbocation. Benzylic carbocation. Okay, so SN1 prefers always second, more than 4, more than 3, more than 1. Is it okay? Easy? Easy. So go back and answer second, more than 4, more than, so the option D is more correct. Okay, chalo. Next question, we'll do this and then we will finish. Careful, as I said, don't panic. Easy questions only. Okay, so what is this? The major product, alcoholic KOH. So elimination reactions, it will form an alkene, correct na? So I have placed, okay. So basically whenever you have alcoholic KOH, it undergoes dehydrohalogenation reactions. Halogenation reactions. It is nothing but beta elimination. So I am taking the molecule here which is there above. This one I am taking. Bromine. This is your bromine. Alcoholic KOH. Excess. And you are heating it. So what will happen? That removes the hydrogen and halogen. Both the bromines are removed. So you'll be getting your pH. And your, okay, shall this one is not extended. This is, I should use my eraser. Okay. This is conjugated and more substituted alkene. Conjugated more substituted alkene. Alright. So this is the molecule. Go back and check this one. So A option is correct. Alright students. Okay, so now students, there are a lot of questions more. Okay, lot of questions. So what I'll do, I'll be sending this in the telegram. Remaining questions I'll be sending in the telegram, as I have a meeting now. Sorry. So I'll be sending this telegram in the remaining part along with the questions. Okay, remaining along with question and answer. Okay, all right. Thank you so much for watching. Please like the video. Please share your video, and WC wants your support. A heart from Vani ma'am. Bye bye. Thank you, and thank you for watching. I'll meet you again with alcohols chapter. So please share the video. Thank you, students.